Just come in. We are about to get started. Maybe close one of it. Okay, then I think we can get started. So good morning, everyone. Welcome to CODAI 2025, the third international workshop on compilers, deployment, and tooling for AI. So my name is Klaiber. I'm with EnChargeAI, and I'm the general chair of CODAI. So before we start, let me give you some key facts. So the CODAI mission actually is to unite academic and industrial AI compiler research and to unite the communities. CODAI is this year taking place for the third time. So, but the very first time actually at High Peak. So we are very pleased, very proud to be at High Peak this year. So the first time was in 2022, actually fully virtual due to the pandemic. Then second year in Hamburg, Germany, and this year in the great city of Barcelona. So we're very glad to be here. So the program we will show you today are 11 amazing presentations by outstanding leaders from industry and from academia, which include original research as well as state-of-the-art technology. So additionally, we will provide proceedings, peer-reviewed proceedings, which are published in the ACM Digital Library. And we are live on YouTube, so the whole world can watch us. Hello to YouTube. And let me also introduce the team. So I introduced already myself. The second co-chair is Sebastian Vogel with NXP. Our publication chair is Andreas Bytyn with Axelera. Marketing chair is Miguel Aguilar in the back taking photos, so great job. And program chair, Dennis Rieber, also with XLR.ai. Thank you very much also to everybody else who helped putting CODAI together. We have a big TPC, a big committee of reviewers who did anonymous reviews. You can see from all over the world, Germany, New Zealand, US, you name it. Thank you to all of you. So a llama visiting an AI compiler conference in Barcelona. A couple of years, this might have been like a joke. If you could think with such an easy prompt, you can generate such a high quality image, and it's available now to the public and it's live. It's just amazing what has been achieved. So if you watch keynotes, lectures, online courses about the tremendous progress in AI, you will often hear two things are key factors to the success, like being able to create such an amazing image. So one is AI model architectures, and the second is compute. I actually claim this is the third one. I'll just ask the audience. Can anybody guess what might be the third one? Money? Oh, good. But we are on a technical conference. Of course. AI compilers, because I mean, without the groundbreaking research and progress of the various AI compiler communities, something like this would have never been possible. I mean, you can have great mathematicians, you can have great hardware engineers. How are they going to talk to each other? So AI compiler communities are actually bridging these gaps. And I think that's why we are all here. We want to learn what's new, what's going on. We want to connect, and that's actually great. And now I don't want to talk too much, so let me guide you through the actual program for today. And then hand over to our keynote. So keynote speaker is Steven Neuendorffer with AMD. Then we will have a short break, followed by session 1, given by Sean Silva with EnChargeAI, Tobias Grosser with University of Cambridge, Shreya Alladi with University of Murcia. Then a lunch break, followed by Andreas Bytyn with Axelera AI, Jan Josef Moritz with Roofline, and Alejandro Martínez with, again, University of Murcia. Followed by another coffee break until 4. Here we have then a number of more university and research-focused papers by Chen Liu with TU Dresden, Alexander Belke and Shubham with Bosch, Max Bonner with Infineon, and last but not least, Ananda Samajdar with IBM. And with that, I would like to hand over to our first session chair, Sebastian Vogel. So give it back, Hals.
So we will have the first keynote by Steven Neuendorffer from AMD. Steven, if I may ask you to the floor here. Steven is a fellow at AMD Research and Development Group. He has been working on early development of compilation for compute acceleration, focused on leveraging LLVM and MLIR. Previously, he was product architect at Xilinx, Vivado HLS, and co-authored a widely used textbook on HLS design for FPGAs, and worked with customers on a wide variety of applications, including video encoders, computer vision, wireless systems, and networking systems. He received the bachelor's degree in electrical engineering and computer science from University of Maryland in 1998 and graduated with honors in electrical engineering in the Department of Computer Science. And he received a PhD degree from Berkeley in 2005 after being one of the key architects of Ptolemy 2. So welcome to stage, Steven Neuendorffer. Briefly share the screen here. Jeez, for that. I need to share, I think, this screen. And it should be down.
Oh, sorry.
1 second. This is working.
Not quite there.
Quite there, but I need to press this button now.
There we go.
Now it should be good. Also online?
It's enough time to, in case I say anything bad, you can censor me. Is that the goal?
Steven, the stage is yours. Thank you.
Thank you. It's really great to be here. I really share this vision that we have a big computer architecture challenge. And part of that computer architecture challenge is figuring out how to program the devices that we have to build in order to meet the requirements of our new AI overlords. So I'm going to talk a little bit about today about how we're programming some of our machine learning devices, and just to, I guess, apologize in advance. Much of this material and a lot of the concepts here are things that have come from other people in the research labs and other people at AMD. So I apologize for anything that I perhaps get wrong or I don't have all of the details about. I can always connect you with the right people who are closest to each particular piece of work. So to begin with, I'm going to talk a little bit about this kind of concept of a spatial architecture, and hopefully motivate a little bit about why we think we need to change the programming models and why we need to develop good tooling to support those programming models. And then I'm going to, I guess, kind of switch gears and go into a little bit of detail about what we're doing with MLIR, particularly to target some of these new NPU architectures, in particular the ones from AMD that I consider to be spatial architectures. So if we look at GPUs, a GPU has a lot of complexity in it. We've got multiple compute units, maybe multiple interfaces to external memory. a lot of on-chip complexity, but a lot of this on-chip complexity are things that can be well abstracted through the programming models that we have today. So if you're familiar with HIP and CUDA, a lot of maybe the difficult parts of programming these devices are things like how do I manage the register file utilization? How do I manage the movement of data between host memory and device memory and the different kinds of device memory? And how you do that is pretty well exposed through HIP and CUDA. And so I would claim that this is largely not a spatial architecture, that you can think of this as a single device and you're programming one device. And you don't really have to worry about how the work that you're doing is dispatched among the different compute units. So you don't really need to worry about where your data is stored in different memories on the device. And clearly the same is not true when we look at the node level. So here on the left is a typical node architecture for an MI250 system. On the right is the node architecture for MI300. And these are kind of different node architectures, but the key thing is that you are no longer programming a node as a single device, right? You are programming this as explicitly multiple devices. You as a programmer have to start to think about where is data going to live, which device's memory am I going to put my data in? And that's true even when we take multiple compute dies and to kind of integrate them into the same package. You have to start thinking about this maybe as a more complicated thing than just a simple single GPU system. And so this concept of kind of spatial locality becomes more critical. So in an MI200 device where I might think of a single compute die, a single level of L2 memory, a single HBM stack, I largely don't have to think about this concept of memory locality. Whereas in an MI300 device, we're starting to get to the point where the device itself is a distributed system. So it's kind of not clear from the picture here, but there's actually multiple dies here with die-to-die interfaces going horizontally and vertically in the chip. And what that means is that if your data is in one of these HBMs, that it can be accessed from any XCD. But in order to get from one HBM device to a different XCD, it has to go across the die-to-die interconnect. And the L2s are no longer global L2s. So in this case, the L2 is shared between the two XCDs in a single die. And so if you fetch data from memory into your L2 cache, then a single die is going to be able to access it. If multiple compute units are fetching the same data, then it's going to end up being replicated in multiple L2s. And so as a result, you as a programmer really need to start thinking about this device as more than just a single HIP or CUDA device, right? You need to start to think about this if you really want to get to the highest level of performance, if you want to get to the highest level of efficiency, you need to think about this as maybe multiple logical devices, or you need to be able to start to control where data is placed and where the corresponding work that's going to operate on that data, which compute units are going to execute that work. So this becomes more complex. It's definitely not the regular sort of clean HIP CUDA programming model that maybe you're familiar with. Or if it is, then you have to start thinking about it more like you would think about programming a node level system where it is distributed and the locality matters a lot. And the thing that I'll sort of maybe present to you as a fait accompli is that this is only going to get worse. As we continue to build more complex devices, as we continue to aggregate more and more in a single package, we're going to end up with more of these NUMA effects where you have to take into account the L2 architecture, you have to take into account the HBM architecture, and where your work is getting executed. And the thing that's really driving this is the movement of data. So in the good old days, we have caches, and we think about caches as being able to move data around, and that data movement is relatively cheap. And in current systems, although we can have HBM stacks, and we can stack a lot of memory very densely into a package and get some efficiencies that way, the cost of memory access is non-trivial. So the cost of getting a piece of data from the DDR bank moving it horizontally within the HBM die, vertically within the HBM stack, and then across the chip to where it needs to go to get operated on is the bulk of the cost of that data access. It's no longer just sort of reading something out of memory, but moving it where it needs to go. And there's sort of two parts to that cost. One is the wires that you need to put down to move the data from one piece to another. And then if I'm willing to put down enough wires to get large amounts of bandwidth, then the cost of driving those wires becomes a power cost. And increasingly, we see that everything that we do in the data center is very power limited. Everything we do in embedded systems is very power limited. And this power is a significant driver. So to give you a sense of how bad it is, this is a sweep of different matrix sizes for running matrix multiply. And so down here, you see basically very small matrix multiplies don't get good compute utilization. They only execute on a small number of CUs. The cost of dispatch sort of dominates the cost of doing the compute. And so you end up getting relatively low performance on a big GPU, right? This is kind of a well-known problem. But we'd expect that at some point up here, we can get to the point where we are using most of the device. And in this case, if you randomly assign where data goes and you randomly assign where the compute happens, then it's very difficult to get up to the highest point. And in fact, we see some outliers down here, which are actually getting very poor compute utilization. And so the solution, if you start to take into account the spatial execution, if you start to think about where memory is placed, you can do much better and you can get much closer to what the device is theoretically capable of. So there's a number of ways that we can think of solving this. So one way that some people have proposed says, I got a good idea. Instead of moving data from HBM all this way into the compute die so that you can do processing on it, let's just move the compute into the memory, right? So people call this processing in memory. There's a number of proposals from different memory vendors about how to do this. People have been looking at this for 10, 15 years at this point. And I guess the opportunity says, okay, well, you eliminate all of this cost of moving the data, and you can process it in parallel because I can put these processing units very close to each bank of memory. That's good, right? And so there is this opportunity, particularly for computation that is very I/O. So maybe not necessarily the prompt phase of an LLM, but if you're doing the generative token phase, you're doing more GEM-V compared to GEM, then there's the opportunity to make use of this massive memory bandwidth that you have. There's obviously some process challenges. You have to end up implementing the compute that you're doing in a DRAM memory process that makes it a little bit less efficient. One of the other big problems is that you start having to think about the compute and where the compute's going to happen and how the data is going to actually get physically laid out in your DRAM banks much more carefully, right? Because in order to make this work, you want to avoid moving data all around the DRAM device. And so to make this work, basically this PIM unit that's doing the computation can only access the data that is in the memory bank right next to it, or the few memory banks right next to it. So now you're suddenly exposing to a programmer not only the fact that I have to think about which maybe large HBM stack my data is residing in, but I also have to think about specifically which DDR bank it's going to go in. And so there's an opportunity here, but there's also a programming cost to be able to get to that, right? So I think this is one of the things that people have been struggling with, trying to figure out, okay, if I am a memory vendor, how do I roll this out to my customers when they're going to have to fundamentally think very differently about how they're designing their systems and how they're implementing them. So I've been talking so far mostly about the data center, and I guess the thing that I want to implant in your mind is that although we have kind of radically different constraints between what happens in the data center and what happens in an embedded system like my laptop, the fundamental problem is still the same, right? So up here, maybe you have relatively large power budgets. I can afford to spend a lot of money because I'm putting something into a data center. But the aggregate bandwidth that I need to provide to the memory is relatively large. Whereas in contrast, if I get down to an embedded system, I still have power requirements that I need to meet. I still have that same fundamental thing. Although the bandwidth requirements are much lower, I also have a cost requirement that's much lower to be able to implement something effectively in a laptop. It's a very cost-constrained environment. So I think that the question is really, are these two situations relatively different? I would claim that they're not. In both cases, we need to start thinking about how to handle this movement of data, and how to start thinking about spatial architectures a little bit more. So what we've been doing at AMD is, instead of building a system like this, where you have maybe your processing cores that connect through a cache hierarchy to a single DRAM in an embedded system, we've been thinking about building a spatial architecture that we call the AI engine architecture that accesses the DRAM of my laptop, but is, in order to be more efficient, in order to make use of the fact that I have to think about, that I'm going to have to start thinking about how data is moved around in my accelerator anyway. We make that very explicit to the programmer to be able to get a more efficient execution. So here, this is basically a tiled architecture, so we can expand it. We can build devices of different sizes. We can scale the compute basically in 2 dimensions spatially. There's on-chip memory that we put in the device. And then each one of these processing columns has access to the external memory of the system. So this is maybe to give you a sense of how this is integrated into a device like my laptop. This is basically a sort of a SoC diagram where you see I have the regular CPU cores. There's the system bus that is connected to the system memory. Still have a GPU in the system. But in addition, along with all of the other SoC IPs that are integrated, there is an AI engine accelerator that exists to perform the same AI computation that would happen in the GPU, but instead to make it happen with lower power. So the idea is, if you're willing to go through maybe the additional effort of doing this, of programming for a spatial architecture, then you can get the power benefit from it. And power is obviously very important in laptops because it directly relates to battery life. So we want to be able to do these new AI workloads and to be able to implement them in an efficient manner. So AMD isn't the only one who is doing this. If you look at a number of different people who are building laptop SoCs, generally we're calling these new accelerators NPUs, or neural processing units. So you can get them in a Macintosh. You can get them from various Windows vendors. Microsoft is really driving a lot of the use cases that they want to expose to the Microsoft users. To begin with, a lot of the applications are basically inside Teams or inside the operating system, where you want to be able to do real-time background segmentation in a video conferencing environment, and to be able to do it without impacting the battery life too much. So in the first version, this is basically the kind of the rough size of the AI engine array that we build. So there's basically 20 compute tiles, there's 5 memory tiles, and then the interface to memory. So if we kind of dig a little bit deeper, I can tell you a little bit more about what the architecture does. So it is this sort of 2-dimensional tile architecture. And so within each tile, you have basically a little processor system. So if you're kind of familiar with GPUs, you can think about this as a little GPU processor. Every core has its own program memory. So every every processor has the possibility to run a different program. It may be that they're actually all running a very similar program. If you're doing something spatially like a matrix multiply, then probably most of the cores are going to be running very similar code. But it's also possible to take application mappings and map them down to this architecture where every processor is running something that's very different. That's something that's kind of different from a lot of the GPU architectures of today, which are designed to have consistent control flow, where every thread is running basically the same program. In the AI engine architecture, you can implement the divergent control flow more easily than you can in a GPU. Every processor also has its own local data memory. There's also locks that allow you to synchronize access to that program, to the data memory, so that different processors can access some locally shared data. And DMA. And the DMA allows you to transfer data further distances in the chip. So for instance, in order to bring data into this chip, we're going to read data from external memory, bring it through the DMA, through the streaming interconnect up into a local DMA, into the local memory of a processor, and then only then can we process it. So again, in contrast with maybe a GPU architecture that you're familiar with, or a multi-core CPU architecture, there are no caches in this device. Everything is essentially a program-managed scratch pad, and either I, as a programmer or as part of the compiler chain, need to manage where data is and how it's moved through different memories in the architecture in order to allow it to be computed on. So the tiles of memory are actually very similar to the processor tiles. They also have DMA as locks and the same kind of streaming interconnect. They just have a large local memory. And then the external DMAs are also very similar. The main difference is that when they make accesses to external memory, they're using device addresses, whereas all of the accesses that are local to a core are only using local addresses. So to implement, when we're implementing programs on an AI engine architecture, what we're thinking about is a lot of the same data movement concepts that you would be thinking about if you were programming a GPU or a multi-core architecture, but we have to start thinking about them explicitly. So one of the concepts is spatial reuse, where we're bringing data from off-chip, and using the streaming interconnect, we can broadcast this data to multiple processors so that there is some replication of data in the device, but what that allows is for each processor to access the data that it needs to process with full bandwidth without stalling for other processors that are trying to contend for the same data. And generally, that's a good thing for predictability. It's a good thing for power and energy when we're developing the architecture. And so there's sort of this trade-off between do we sort of replicate the data multiple times in different local memories or provide shared access in the AI engine architecture. We sort of lean to the side of replicating the data and avoiding that on-chip contention. Another sort of pattern that we see a lot is temporal reuse, where we bring data on chip and we store it in the large memory tiles and then reuse that data multiple times over time. So maybe I want to store part of a matrix, I bring it on chip, and in order to avoid the power cost or the bandwidth cost of bringing it in from external memory again, we keep it in the local memory tile. Another common pattern is using the on-chip memory for buffering. So we can take data from one processor, and instead of writing it all the way back out to DRAM, we write it into the memory tiles, store it for a short period of time before it can go into the local memory of another core and be processed. So these are some of the kind of common patterns we see in applications, and it is often very useful for us as programmers to sort of think about, well, what are the programming abstractions that we use when we're programming these common patterns? So what we've been trying to do is to take those programming patterns and build them into a compiler stack. So we bought into using MLIR very early on. So we use a lot of open source software from LLVM. We build up abstractions on top of that in MLIR. We leverage very heavily a lot of the work that's being done in the open source community to connect to the programming models that people care about, like PyTorch. We invested very heavily early on in building up the PyTorch MLIR story. There's now a lot of people inside AMD who are working with IREE, and we've taken those kind of front-end technologies and connected them to the back-end technologies. So mostly what I think about, what I focus on, is how do we take these kind of common abstractions like linalg and lower them down to the device that we have in a very device-specific way, right? So it's different enough from what we have to do in the GPU world that it seems like we need a new set of compiler abstractions to be able to target AI engine devices. And yet, at the same time, we also want to be able to leverage as much of the existing technology as we can. And so we also want to build programming models that make AI engines and GPUs look more similar, that will help simplify and find more commonality between the different tool chains that we have. So we don't have to build up a large set of technology just for AI engines and then a completely independent set of technologies when we're targeting GPUs. And then obviously at the lowest levels, we want to use other good kinds of open source infrastructure. So for code generation, we have an open source compiler that targets the vector VLIW processor that's inside each tile. We use that for doing the local code generation for a tile, and also leverage other pieces of open source infrastructure from AMD, like the HSA backend, that allows you to specify the runtime behavior of how the host is interacting with the device and be able to dispatch work to an AI engine device, and in the same way, using the same APIs that you would if it was a piece of GPU that you were dispatching work to. We do have this single core compiler. It's called Piano. I think maybe for those of you who follow LLVM, maybe you saw the announcement a few months back. I think the sort of the big new addition to the work that we have here is now support for the newest version of the AIE architecture, which is in the new Strix Point devices. So that's as of a few days ago, we pushed that into the open source. None of this is actually upstream yet. I think one of the things that we'd like to do is to get to the point where the community sees that there's a lot of interesting technology here, and eventually we can upstream it. But right now, the focus is just in getting it out on the open and enabling people to use it. So if anybody's interested, I'm happy to put you in touch with the people who work on this on a day-to-day basis. I managed to get to this point in the talk, and I haven't actually showed you any MLIR. So since I advertised that this was going to be a talk about MLIR, I'll show you a little bit about the MLIR abstractions that we use. So at the lowest level, there's this MLIR AIE dialect that we use. And basically the idea is to represent exactly in a one-to-one structural way what the architecture concepts are in the programming model. So you can essentially program every bit in the device through MLIR this way, and the idea is to expose everything at a very, very low level. And so, for instance, here's my the tile inside the architecture. So it has a processor core. So this is basically just MLIR code that will get run through LLVM eventually and generate code that runs on the vector core. So there's, maybe if you're familiar with MLIR, there's not going to be a lot of completely new things there other than the device-specific dialects that we need to generate good, efficient vector code for this architecture. So just like, there's a GPU dialect for generating GPU code, we have a vector dialect that allows us to directly target the vector instructions of this instruction set, and lowerings from the high-level generic architecture independent vectors in MLIR down to that instruction set. And then there's the DMAs, and so memories in the DMAs. So for instance, we need to take pieces of data, a buffer of data that you're going to be processing, and we want to be able to assign it to this memory, right? So this basically just generates a a memref, but instead of being in host memory somewhere, it's associated with a particular tile, a particular memory inside a particular tile. And so this is basically the way that we build up the lowest levels of the abstraction, and basically you can change which tile you're referring to, allows you to move data allocations around. It allows you to move code allocations around to different portions of the device. Sort of the next step is, well, you want to be able to reference a memory from different tiles. And so built into the dialect is a bunch of validation rules that allow us to easily check in a piece of IR whether we are following the access rules of the architecture correctly. So in this case, I have two tiles, and because the fact that these tiles are neighboring to each other, I can have a piece of code that accesses the memory in both tiles. There's also this streaming interconnect in the device, so this allows us to transfer data, and in each tile, we can individually program the connections in that switch box in the streaming interconnect. So if you're familiar with FPGA architecture, this is a lot like the connections that happen in the switch boxes in an FPGA. And part of the MLIR dialect allows you to directly make these connections inside the switch box. Obviously, if you're thinking about this at a very detailed level, maybe that's interesting, but for most of the programming applications, we don't actually care about exactly what happens in each switch box. And so we do have, this is where we start to have higher level abstractions in MLIR that implement basically connection routing of these streaming connections from one core to another. So we introduced the concept of a flow that allows you to make a logical connection from one point in the streaming interconnect to a different point, and then a pass that processes those flows to generate the detailed routing inside the device. So moving on, we also have these DMAs, and essentially each DMA is its own individual processor. So instead of executing compute instructions like the vector processor is going to, the DMA is executing data movement instructions that either fetch or store data to the local device memory and then push that data onto the streaming interconnect. So again, we sort of basically reuse a lot of the existing infrastructure in MLIR to represent control flow while using our own device-specific dialect to represent the individual DMA operations. So that sort of kind of maybe gives you a sense of how we're using MLIR at the very lowest level. And for practical designs, it's very difficult to, there's a lot of things that you have to think about in order to program all of the components of the device so explicitly. And so in MLIR, we built up kind of higher level abstractions that hide some of those details and lower in the sort of standard MLIR way, where you're taking high level abstractions and turning them into lower level abstractions to try to hide some of those details. So one concept that we use very generically in a bunch of different places to abstract the notion of buffers and locks and data movement is a concept called the object FIFO. And basically what this allows you to do is to send a tile of data from one processor to another processor, or from one processor to many destination processors. And so basically what an object FIFO does is it abstracts the data allocation of data within a memory. So when you acquire a buffer from the object FIFO in order to write into it or in order to read from it, the object FIFO returns you a memref. And then you can process it, and then eventually you will release the memref that says, okay, I'm done using that, and so continue on. And I'll sort of go into a little bit more detail, but basically the key idea here is that this high-level object FIFO concept can actually map into a number of different lower-level representations. So if I have a system where I have two processors that are next to each other, then that object FIFO communication can be implemented using local memory references. Whereas if I have a longer distance communication, then I need to turn it into a different pattern. It's actually more complicated. I'm going to need multiple buffers. I'm going to need multiple DMAs, multiple locks in order to implement that communication pattern. And the object FIFO and the lowering of object FIFOs into the lower level representation basically hides that complexity for you. Another thing that we've been doing is taking the MLIR and exposing it to programmers in Python. So mainly this is a kind of a syntactic convenience. It's that it's easier to use Python to represent the MLIR code for most people than it is to start hacking away at MLIR directly. I recognize, I see Sean as desperate to see what the Python looks like. But you know, I don't actually expect you to read what's in here. Basically, we're just using the MLIR Python bindings to take the MLIR operations and just expose them into Python. But you know, basically, this represents the data movement, and then we can either represent the specific computation on a core by calling a library, or maybe calling out to some C code, or in Python having, you know, the detailed MLIR operations. Maybe you can read this better, Sean. But basically, this is that same object FIFO operation that I showed you before, but more with a little bit with the Python syntax instead of the MLIR syntax. And so maybe to give you a little bit more detail about what the object FIFO is actually doing here, here we're going to process these three buffers in sequence, and each time this core is going to produce one at a time. So it's going to produce a tile, acquire a tile so that for production, so that it gets a memory reference to it, and then it can access it, and then it's going to release that buffer so that the receiver can access it. The API also allows you to do more complicated things, like to manage multiple buffers at a time. So in this case, maybe the consumer says, well, I want all three of I want to receive all three buffers as an atomic operation. So here it can acquire 3 buffers at a time and index into them, and then release all 3 of them and say, I'm done with all 3 of them. You can also kind of mix and match these. So maybe what you're doing is you're processing a window of 3 buffers at a time, but you're kind of going to shift as you go. And so you can maybe you're only releasing 1 buffer of the 3 that you're using, and you're going to reuse those other 2 buffers for the next operation, for the next iteration through the execution. So object FIFOs will sort of take care of a lot of that bookkeeping under the hood. We also added some of these communication patterns that I talked about a little bit earlier into the object FIFO. So for instance, you can have an object FIFO that has one producer that's doing broadcast to multiple destinations, right? So the object FIFO will just hide all of the bookkeeping machinery behind the scenes. And also, if you're reading data from external memory, some of these patterns that go through the memory tile are also just sort of natively dealt with by the object FIFO abstraction. So you can read a large block of data from external memory, bounce it through the local memory tile, and get some of these reuse and distribution patterns from the on-chip memory. So basically, all of that sort of gets hidden inside this buffer acquire and release mechanism that the object FIFO provides. So you know, that's the kind of low-level detail where we're thinking about this from a programming model perspective, from a mental perspective of how does each one of these cores operate independently. But for some operations like matrix multiply, it's actually more natural for the people who are programming this to think about how does the device work as a whole. And so we've been thinking about higher level abstractions that instead of saying, well, you know, every core is doing this independent operation, I want to be able to say, actually, well, there's this kind of common code that is running on many cores at the same time. And it seems like this is actually a very different programming abstraction from the perspective of the way people are thinking about it. So you know, here is sort of pseudocode, and I guess the rest of the story is kind of how do we take this pseudocode, which is maybe a device level concept, and lift it up to the point where people can program it that way. So the programming model that we've been thinking about here is called, we call it AIR. And the idea of this is partly to, you know, think of this higher level abstraction for the spatial computing and AIUs, but also to think about how these spatial computing concepts for AI engines are actually somewhat in common with what people want to do for GPUs. So I'll maybe give you some examples about what the how this works without really going into too many of the details. But fundamentally, what we think about when we're thinking about these spatial computing engines is that there is some memory hierarchy. Sometimes we have maybe the local memories. Let's think of that as L1. Maybe these can, I have some two-dimensional array where I can have some neighboring access of L1 memories. Okay, this sort of acts a lot like how GPUs work. If you have shared L1s, it's a lot about how AIs work because there is some local memories that you can access locally. We also think of the other levels of memory hierarchy, like the L2 memories, where maybe they're shared among a large number of compute units. That's something that the GPUs seem to have. It's something that AI engines also have. We have the level of memory tiles. We call that the L2 logical memory. There's also the global memory. There's the device memory. Maybe in some cases, like GPUs, maybe this L3 memory is also itself partitioned, and there's some locality that you need to be able to represent there. And then the question is, how do I represent the compute? So we have this concept that we call a herd, and a herd is basically, you can think of it like a GPU work dispatch, where I have a number of pieces of compute that I'm going to execute, and I'm going to do the same thing on all of them. So here there's some common code, and I'm going to execute this on some maybe 2D array of processors. And here there's sort of a divergence maybe from what you're used to. If you're used to thinking about GPUs, and you're familiar with how streaming computation works in GPUs, it's very difficult to guarantee that two different GPU dispatches are actually co-resident in the GPU at the same time. So we have a constraint when I launch this piece of work that both segments inside this launch must be concurrent in the device at the same time. So here, maybe there's a two-dimensional array of work over here and maybe a one-dimensional array of work over here, but I want to be able to stream data from one to the other. And the requirement there is that both of these must be co-resident at the same time. There are also cases, so in order to represent that streaming computation, you kind of have channels, and channels themselves are something that maybe you think about them as arrays of logical channels, right? So here I have a 2x2 array of channels to represent the kind of multi-dimensional communication from one set of computations to another set of computations. And then occasionally, maybe when I launch things, I say, okay, well, there's multiple things that I want to launch, and they're all going to be doing the same computation, but I don't actually need them to be co-resident. I'm not necessarily going to stream data from one to the other. Or if I am going to stream data from one to the other, I'm happy going through, let's say, external memory to implement that communication. And so there's a concept inside the launch that allows you to basically replicate the data launch that you're happening multiple times. And if you have a big enough device, maybe you can dispatch those dynamically on different parts of the device. They could be co-resident, or maybe they are not co-resident. So here I dispatched this piece of work, but there was no other place for the second dispatch to get dispatched. And so we had to wait for some of this to finish before we could go then allocate some resources in the device to do another computation. So this is maybe some of the concepts that we need for spatial computing that are kind of common between AI engines and GPUs to sort of maybe show you how that pseudocode can be turned into this work dispatch. This is basically a set of dispatches inside a launch that are concurrently executing on multiple DMAs and multiple AI engines in order to bring in multiple tiles of data, broadcast some of them horizontally, broadcast some of them vertically in order to do essentially an output stationary matrix multiply tiling across multiple AI engine cores. So to conclude, I think this concept of a spatial architecture is something that's going to be around for a while. And I think that's true whether you're looking at GPUs or NPUs, or maybe some of these new PIM ideas come out. We're going to have to start thinking more explicitly about data movement, and that is not just at the distributed system level where you're dealing with networking and network data movement and RDMA and SmartNICs and things like that, but all the way down to the device levels in the GPU and even into an embedded accelerator like the NPU. And so our current focus is really on the NPU right now, but clearly we see a need for some commonality between this and the GPU. And so you sort of maybe end up with a situation where you have kind of a hierarchy of MLIR abstractions, but each one of these MLIR abstractions are also things that we can expose through Python bindings. So I think one of the I would say challenge problems that we have right now is maybe the challenge of how do we take this and sort of explain it to people who are going to use it. Would we rather have people building up more abstractions inside MLIR and say, hey, let's continue to build up very deep abstractions in MLIR, or should we give them Python bindings at a relatively low level and then build up all of the complexity with more and more complex Python bindings? So I would say right now, from a research perspective, we're doing both. There's times when it's kind of natural to say, okay, let's take the Python and give people Python extensibility, mostly because the people who are probably able to do that Python extensibility are different from the people who are going to be able to build new compiler passes. And at the same time, I think we have this kind of next generation GPU question of how do we take this and sort of lift it to the distributed GPU programming problem. I don't think anybody in MLIR has really looked at that. So maybe as a kind of a discussion topic, I think we have a workshop format here. Maybe one of the questions that we can discuss is, how would we sort of build up a good distributed computing compilation story for GPUs? That's the end of my talk. I'll leave you maybe with a last slide. If you're interested in any of this, there's a lot of public information. Again, all of this is open source. You can get access to all of the MLIR dialects. There's some things that if all you want to do is go read a paper, there's a paper about how to do this with the NPU architectures. There's a lot of hardware that's available. You can go buy it, or if you talk to me, we can give you access to it in the cloud. So you can just log in remotely and access a processor that has an NPU in it. So thank you. Are there any questions?
Amazing, very nice talk. As you can say, this is a workshop format, so we have some time for questions. Are there questions from the audience? We have a microphone here that I will then hand over. I have a question on the memory model. So we have this L1, L2, L3 kind of hierarchy, but how do we expose the fact that the L3, the global memory, is not uniform? So it might be, 2 hops away from your current point.
Mm-hmm. Yeah, so in the MLIR-AIE dialect, we don't need that today. So we simply haven't done it, right? But there's, in the same way that we represent the partitioning of data in different compute tiles, where you have buffers that are assigned to particular compute tiles, it seems pretty natural that we can take that and have tiles of L3 and then assign buffers to different, explicitly to different tiles. Now, I think the bigger question is maybe how do we start representing some of these affinity kinds of things in the AIR dialect? And that's not something that we've looked at, right? We know that this is a problem. We know that it's important in GPUs. We just haven't gotten to that. Right now, we're a little bit more focused on NPUs, and so we haven't quite gotten there yet, but I think it's definitely something that we need to be looking at.
Any further questions?
So, in the sort of compiler space, there's always been a problem around scheduling would be how I describe it, but you had that where you have this problem being distributed with lots of workloads and tiling to the GPU. I've seen many approaches to this, auto-tuning, auto-scaling, all of these sort of things. Where in your stack do you envisage we go from this abstract computation to finding an actual mapping to the hardware?
Yeah, so I would say right now, both in MLIR-AIE and in MLIR-AIR, the scheduling is explicit, right? So you're building something which is a device-specific mapping where you are expressing that scheduling decision. And we haven't really looked at how might I take a a truly device-independent representation and map it down to that. I would say the place where that comes in right now is in the transformation of linalg into the MLIR. So I would say our assertion so far is that the problem space there is really well represented by taking linalg and tiling it. Or if you think about taking like nested affine loops and doing tiling of nested affine loops, that expresses the design space that you need to do to be able to express the scheduling problem. And then it's if I've explored the space of all different loop tilings, then I only have to pick the right one and then translate that loop tiling into a device-specific representation. And so it sort of comes in that linalg to error lowering.
Thank you. Maybe my question is based on this mapping and scheduling problem, because I see that you show some tile size of the AIE core, and I see this embedding memory, which is only 64 kilobytes, and it seems that this is so many small cores in this NPU core. And our chair also IC lecture, and we also design multi-processor system. And do you have any comment or does AMD do some research into this trade-off between many small cores or relative big cores? Is there any observations on this that you can share?
Yeah, so I mean, maybe there's a few things that I can say. So one is that you're right, the local data memories aren't that big. And the assumption is that you're always bringing in new work into the L1, and the kind of on-chip reuse opportunity is the L2 memory, right? So we would rather make the L2 memory bigger and use it to represent the sort of on-chip reuse, rather than having that reuse happen in the L1 memory, right? So the L1 is basically big enough where you can bring in 2 new tiles of work while you're computing one and reading out a third, right? So you can do everything fully pipelined. Now, I think from a granularity perspective, the cores that we're building are relatively large granularity. And that seems to be a balance between, do I build like really big matrix operators, like a TPU, where you're building, maybe 1,000, 256 kind of 256 by 256 matrix units, is definitely kind of at the larger end. I would say the assertion of the AIE architecture is that that's too large for a lot of workloads. It doesn't give you enough flexibility to take these relatively small pieces of work and to partition them. At the same time, I think if you get to the other extreme, where let's say I have a large number of scalar RISC processors, then you have too much control overhead for the amount of compute that you're doing, right? So I would say AIEs live in the middle. And maybe it's a middle that exists because we are taking an opinion, and maybe it's a middle that exists because both of the extremes seem bad, and living somewhere in the middle is a good thing. And in the sort of architecture explorations that we've done, that's seemed like a good granularity. I think definitely one of the challenges we have moving forward is that if you look at the different NPUs from different device manufacturers, they all look pretty different. And it's unclear whether that, which one will win out, I would say. Ultimately, I think we need to figure out what are kind of the fundamental concepts that people latch onto. In computer architecture for a long time, I think, it's kind of dating back to the IBM 360, we've kind of hit upon a few programming abstractions like virtual memory that seem to work well enough for a very long period of time. And we clearly haven't gotten there with AI. The field is just moving too rapidly, and there is not a lot of agreement on what the programming model is if it's not CUDA. Right? And I would say a lot of what the NPUs are is I would say an assertion that for some kinds of AI, CUDA is not the right programming model.
I hear we have one last question from YouTube. Michael, would you like to ask that?
Yeah, I mean, it's great that we are also getting some feedback from all around the world. So the question is by Emily Solars, and what she wants to know is, how do you pick the tile size? Are you using IREE's auto tuner? Are these choices done manually by the programmer right now? Are you using exhaustive search to pick your tile size?
Yeah.
Well, more than one question, but let's see how.
Well, I think it's kind of all this. I sort of see it as the same question, and I would say it's really one of abstraction, right? So, to tell you the truth, a lot of what we do right now is actually relatively low-level programming, and we don't need to have something that figures out the tile size automatically. Because for a lot of what we're doing, we're still not to the point where we're really trying to go through that whole compiler chain, right? There's a long, tall stack that needs to happen to make that work. And in order, kind of the short-term pragmatism is always balanced by the long-term, well, we'd like to have this large vision, right? So I think there's definitely an opportunity to explore a lot of different compiler problems. And one of them is, how do I do the right tiling? What's the right tiling? Can I get to the right tiling in one shot, or do I need to do a big design space exploration of different tile sizes and different loop tilings at the lineage level to explore that design space, right? So I would say, right now we haven't been very opinionated on the right way to solve a lot of these problems, and instead our focus, and honestly, a lot of the reason why we're putting this out in open source is to give kind of the basic framework for a lot of these problems to get expressed, and then to work with people in the community to come up with optimal solutions for them. And my experience is that even the optimal solutions are usually a trade-off between what can you do fast and what can you do with highest quality of result. So I think even in there's a large range of different opportunities, and would be happy to talk with people about what they think are good ideas. And I think there's a lot of research potential there for people to do interesting publications and research and PhDs and all sorts of things there.
Fantastic, Stephen. You just mentioned talking with others about exactly these topics. We have now the chance in the coffee break to continue exercising this workshop and asking potential further questions and have a great discussion. See you in, I think, 25 minutes from now.
Thank you.
You guys are like working like bottom up, like
Okay, then welcome back after the first break that we had today with coffee. We couldn't have coffee earlier this morning, but now I see there's a couple of coffee mugs in here. That's pretty awesome. So welcome back to session number 1. I'm happy to introduce you to Jean Silva, who graduated from Purdue University with Bachelor's of Science in Mathematics and Computer Science in 2014. And afterwards joined Google, tackling compiler, runtime, performance, and usability problems. And joining Google, I think, in the Bay Area, and recently moved to Germany to join EnChargeAI. What's important and very much in context also with this conference here is that he's the initiator and maintainer of Torch MLIR, which is one of the most used dialects in the MLIR space. We are happy to have you here today. Welcome to the stage, Sean Silva will give a talk on practical discrepancies in, and I can't see the rest of the title, in AI performance. What else could it be?
Thank you. Thank you. Hi, folks. So, yeah, I think one thing that, as Michael was saying, a lot of what we do is connecting hardware and models. And those two things have to come together in order to have a working system. Oh, there we go.
Yeah, focus needs to be here. Is it working? Yeah.
Yep. Okay, cool. And I think there's this kind of disconnect, because sometimes we think like, oh, our hardware is this fast. But in reality, hardware is never this fast. Hardware slowly gets fast as software catches up with it. And so I'm going to try to convince you that there's really no such thing as like the performance of your hardware here. And really, performance is something that is kind of continuously delivered by software. And the only way to achieve that is basically by having a sustained velocity from the software targeting your hardware. And of course, hardware can be designed to make that velocity higher as well. But a lot of it really boils down to how you design your software. So to do this, I'm going to cover a few high-level topics. So first, there's going to be two mental models around how to sort of think about this problem. And then we'll combine them and then look at how LLMs enter the picture and how they affect things. And then at the end, I'll just give a list of things from my experience that we can quickly run through that hopefully will ring some bells and stimulate some discussion. All right, so without further ado, first mental model, cost quality intercept, I call it. So, again, as Michael was saying, actually, I couldn't have planned this better. You have AI models and AI hardware. And they're both getting better at an approximately exponential pace. And so when you look at this, like just this very simple equation, like, you have some notion of model quality for a certain amount of compute, and then that's what the model gives you. Then you have some amount of compute, which comes at some cost. That's what the hardware is giving you. And, when you combine that, you get some amount of quality at a certain cost, and that's exponential. So let's just visualize this a little bit. 1 second, let me move this. So the first trend, on this plot, basically the horizontal axis here is time. So as time goes on, and then the vertical axis is some notion of compute. So like in this case, the compute required. And so basically what happens here is that you have some amount of compute that's required to get a given model quality. And to give you an idea here, so for example, Llama 1 versus 2 was about a 10x reduction in compute required for the same model quality. Llama 2 versus 3, same thing, about 10x. And so, this is on a log scale also. So this goes down exponentially. Great. And then, the hardware and some abstract notion of, datasheet specs or whatever, keeps getting better at the same cost. Again, horizontal axis here is time, vertical axis is the compute that you have available at that time. Now, any given application, whatever you're doing, is going to require a certain quality and a certain cost, right? So it's like if you're trying to do image recognition for your product, maybe 90% accuracy is enough. Maybe 99% accuracy is needed. Maybe 99.99999% accuracy is needed. So depending on what quality you need, there's going to be a certain cost, which is how much compute you need to get it. And so let's combine these two. So here you can see that the compute required to achieve a certain quality is going down. And then the compute available for a given cost is going up. Right? Because the application, it's like I'm trying to sell a phone that costs this much. So, the cost is usually a fixed thing, and the application quality is also a fixed thing. And so for a given application here, there's a period of time where the application is infeasible to deploy. Like say ChatGPT was infeasible to deploy, even if we had the model, until the cost was low enough on the hardware side. And then after this intersection point, then the product becomes feasible. And this is where the magic happens, because this intersection point is really critical. Because it converts all these notions of compute into time. Like this is when that product becomes available. And so when you think in terms of like what AI hardware is really, let me see if I can move this thing here somewhere. I don't have a good place to put this. Okay. Anyway, it says better hardware makes AI products happen sooner. And really, like all you're doing with better hardware is shifting this time point where people can deliver things, right? So it's like fundamentally, like when people are, no, it's all right. I can just read it off. And so when you think about it, like really all the hardware is doing is just moving this line up so that so people can, do what they want. Like maybe people want to make $5 profit for every 1 million, tokens or something. Well, they can only make $5 profit with 1 million tokens once the hardware gets this good. But if you give them better hardware, well, they can get $5 profit per million tokens, sooner. And so that's why they buy your hardware, because they want to make $5 profit now instead of a year from now. And they really don't care about compute, right? Like from their perspective, it's just an implementation detail to get a certain quality at a certain cost. And one point here is that, we're talking here about hardware, but the models keep getting better, right? So they can just wait, right? They always have the option of just waiting. Okay. And then here's like the harsh reality though. It's just that the kind of performance achieved here, which I am like underlining here. So the performance that you actually achieve is never like the theoretical datasheet performance. Oh, perfect. Thank you. Thanks, Andreas. Save the day. And so the achieved performance lags your theoretical performance. So like say you have a chip that you think has like 100 tera operations per second, but maybe you're only going to get 50 out of it or something. And that means that your actual intersection point with the model is later. So this counteracts that thing, right? So you have the we can go back a slide. So your hardware is like theoretically better, so you get an earlier delivery date, but then you don't really get the full performance of your hardware. It gives you a later delivery date. So those two things are at odds with each other, and one needs to be better than the other. So what this all means is that when you really look at like from the customer's perspective, they don't care about your theoretical performance. They only care about this achieved performance. And so from the customer's perspective, as I was saying, this really manifests as a time delay of where they are, when they're going to get that performance they want. But from your perspective as a systems person, you're always going to see this as your hardware is being underutilized. So I think the point here is to always like, at any point in time, you're thinking, oh, my hardware is only getting 50% utilized, or my hardware is only being 30% utilized. Then that actually means you need to move faster, because that's what's going to actually get you the performance. So let's dig into that, why it is that moving faster gives you performance. Because the reality is that the achieved performance comes in 4 phases. So it's just a given, right? There's some amount of time before an AI model runs on your hardware, unless you're NVIDIA. And then it's probably been co-optimized for them. We'll come back to that later. And so there's an initial period of time where it's just not even running. And then eventually it runs, but it's not that great. And you spend time optimizing it, and then you stop optimizing it because you're out of time. And then that's your final performance. And so let's look at what this looks like. So on a chart here, so the vertical axis here is performance and the horizontal axis here is time. And up here you have like whatever theoretical performance you think your hardware can in principle deliver. But in reality, there's this delay here at the beginning, then you get some performance, then you optimize it, and then you stop optimizing, and then boom, here's your discrepancy. Like I claim almost every reason that your hardware is not performing well is because of this one thing, right? It's like, yeah, like anytime you have a data sheet number and it's not high enough, or like, and like your real number doesn't meet the data sheet number, it's because of this phenomenon. And so that means we have to optimize, these factors. So things work at all delay. So like the best outcome here obviously is it just works, right? Transparent software layering. In practice, a lot of our hardware designs mean that it doesn't always just work because we're making some hardware trade-offs which are not as general. And then that means that there's like extra work to express the program on our hardware. And, believe it or not, good documentation, is actually a huge part of this, right? Being able to actually move fast requires good documentation. You need a good compiler with clear diagnostics when things go wrong. You need to be able to debug things. You need high quality simulators and APIs that are familiar to use. Like each one of these, like if you think about it, it's like if I told you, like, here's a chip that has performance X, and here's a chip that has performance X times 2. All other things being equal, if I told you, well, the slower chip has a debugger and the faster chip doesn't have a debugger, you would probably choose the slower chip, which tells you that a 2x, having a good debugging story is worth about 2x performance. And each of these individual things, right? It's like, banging my head against the compiler, for multiple days with some weird crash inside the compiler, some obscure error. Like people would rather just take the lower performing chip than to deal with that. And then, yeah, so this other component, this optimization rate, everything that we mentioned before is useful. But here, and I loved Stephen's talk, where it's like really having the ability to fall back to like lower level, higher performance or more control, APIs with more control is really critical, because then it's like you have your compiler that handles like the 95% of case, but then like the 5% of cases that are like super hot, you drop down to a lower level, and you can, like, because they're so hot that it's worth spending the time to optimize those. And of those, 5% are like ultra hot, and then you drop down another level to really get, everything you can out of those. And like that kind of multi-layered, kind of inline ASM, let's call it, is really critical to achieve high performance in practice. And then yeah, profiling tools. That's another one where it's like, if I told you, here's a piece of hardware, here's another piece of hardware. This one has a profiler. This one doesn't have a profiler. Like, it's like probably worth a pretty substantial amount of performance. And then, yeah, this out of the box performance is actually one of the most complicated ones, but it usually is like, roughly speaking, it's, a factor of how, kind of the general design of the compiler and system software, which is like, you need the general case to be like decent, and then, enough like important, in quotes, special cases have to be optimized that like in some statistical sense, you hit those special cases, reasonably enough. Oh yeah, and they can't be hacks. Yeah, because they can't slow down the rest of the system development. So this actually comes back to the fundamental theorem performance, I call it. Hats off to Newton for like the fundamental theorem of calculus here, but really, I think this is just a mathematical fact, right? Like, I mean, it's just your performance at your delivery date is equal to, how like your performance at your start date plus how much performance gain you get per week per engineer from your start date to your delivery date. Like, this is your entire performance summarized in, in one equation. So yeah, that's velocity is super, super important. Okay, so let's combine these two. So we kind of glossed over two things. So Number one is that the theoretical hardware line is actually discrete, right? It's like you're not coming out with a chip every day. It's like, every some period of time. And then, the achieved performance, as I showed on the last slide, is like a more complicated function that varies over time. So this is really what like an accelerator project really looks like. So you have like multiple discrete generations of hardware, and then you have models. And like maybe for generation one, it's slower to get it even working at all. It's like pretty slow compared to what your hardware can do here. And then your, it takes you a long time to get to the final performance. Whereas as you mature, these lines converge so that the time it takes to get running by Gen 3 is like super short. It's pretty close to the final performance even from day one. And then in a very short period of time, it gets optimized. And so, this actually is like the sign that you're doing things right. And the alternative here is that, as more models come and your hardware evolves, actually like the situation gets worse. And that's basically where hardware projects go to die, frankly. And I've seen a couple of them. So yeah, this is like converging these metrics is super critical. So you have to get the time it takes you to get a model up and running at all, the out-of-the-box performance, and then how quickly the models can be optimized. Like really, if these metrics don't converge, like you're toast, is my experience. And so really, just as much as your hardware is designed to improve performance, like, your hardware methodology is designed around optimizing, ops per watt or whatever it's doing, your software methodology has to be designed to improve these three metrics. And it's like ultra critical. All right, so that being said, let's talk about why LLMs pose a unique challenge for hardware. So here's just like a fact. So in 2024, there was an 83x reduction in cost per token at the same quality. Some of that, depending on how you measure, came from hardware improvements. But bottom line, it's well north of 10x improvement just from the model architectures alone in 2024. And, you can actually trace this back even a couple more years. Llama 2 versus 3, it's 10x. Llama 1 versus 2 is also 10x. And then these days, like a 1B class model can easily beat the original ChatGPT. And so, this rate of progress is something that we have not seen. So to give you an example, like for in ConvNets, it was something like maybe 2x per year, like 2, 3, 4x per year, not 10x per year. And so this is like a really 2x per year is a strong exponential, but this is like an insane exponential. So what does that really mean for us? So if your hardware is like when the LLM are improving so fast on the model side, your hardware needs to be really compelling to be worth it. Not just compelling, but like really compelling. And it's kind of like the opposite of Moore's law, right? It's like, imagine back in the heyday of Moore's law, where it's like things are magically getting so much faster every year. It's like, why would I even bother to optimize my software? So now it's turned around, right? So it's like, why would I even bother like buying faster hardware when I can just sit around and let the models get better and, maybe upgrade to the latest, this is the next generation of the hardware I already have. And like the key thing here again is bother, right? Which, is a function of how much performance you're getting for how much effort, which again comes back to your software stack. So as like a rough rule of thumb here, just based on like those facts that I put I'm just digesting those numbers. 3 months of model improvements is equal to 1 year of improvements on the incumbent hardware. So this means that if you are delayed 3 months from state of the art, like it's like you're competing against like next year's GPU, let's say. And so the fact that the like call it like NVIDIA or whatever, like, that the incumbents are co-optimized for the models from day one. So they may actually, like the model was running before even the official release, right? And it's been co-optimized. That whole process I was showing has already happened for the model by the time it's publicly released. And so it's a huge advantage, right? Can easily be 3, 6 or more months of co-design that's been done there. And so like, just as like a simple thing, like if your hardware release date's a year from now, like you're not actually not competing against next year's GPUs, let's say. But if your software is lagging by 6 months, then you're actually like really 2 years behind the incumbent hardware. And so that's like it's really hard to overstate how powerful that is. And so let's like correct our previous slide. So here we're showing in this slide qualitatively, right? We were showing that these lines kind of have similar slopes, but in reality, it's like this. So like the compute required for the model is about 4 times faster. And so it's, really there's this compression of like, whereas like here, there's kind of like a decent, moving up in the delivery date. But because the models are getting better so much faster, it's actually not that much sooner, which means that this is a mouthful, but the compellingness per unit performance advantage is way less in the LLM space. And trailing the state of the art really quickly negates all your performance advantages. So here's an example, right? So it's like if you're delayed even by this like tiny amount, right? Like just this small amount here, it like can really make up for this like large dip. So see here that the hardware lines are like very separated. Like here it's like, wow, like in principle, you're like, this huge distinction between like the horizontal intercepts here. Whereas this tiny delay totally negates all of that on the model support. So you have to be really on top of the latest models. And like, let's just put this even more quantitatively, right? So it's like 10x improvement per year, which again, I think the number is actually possibly higher than that. That's like about 1.77x for a 3-month delay, which means you lose 1.77x every 3 months you trail the state of the art. And additionally, incumbent hardware is getting better at a decent rate too, so basically you're losing like 10 to 30% performance advantage every 3 months. And so like in total, you're actually losing, north of 2x performance every 3 months that you trail, what is like, the incumbent hardware's state-of-the-art public, solution. And that's crazy, right? It's like Moore's law, we were talking about like 2x every 18 months. Here it's like 2x every 3 months of performance. So like, I think the key thing here is it's a marathon. It's not a sprint. It's not like, oh, great, I'm running this state-of-the-art model. No, the state-of-the-art keeps moving forward. And so you have to actually sustainably keep moving forward, right? You can't just have a hack where you're running, this year's Llama, just in this hand-coded assembly thing that happens to work. Like you have to be ensure that like once that model is running, you have to take the next model and the next model and the next model and the next model. And like basically this, as I was showing this, like achieved performance has to match the theoretical performance, and they have to stay close in perpetuity. Just to go back to this diagram here, when we actually look at it, you might like naively look at this and say, oh, well, generation 1 is only trailing by this much, generation 2 is trailing by this much, generation 3 is trailing by this much. But actually, this is not the right way to look at it, because the reality is like Gen 3 was delivered the performance, even though, yeah, it's great, the performance is closer to peak, but it's also happening way sooner, right? And so like the real way to see it is like this. And so basically the time delay, right? The fact it took Gen 1 almost like a whole hardware generation to deliver on its performance, right? Whereas Gen 3 took less than, solved it very fast. Gen 3 is getting essentially like a full generation hardware performance from the earlier delivery date. And, and that's huge, as I was saying. All right, so that being said, you might say like, well, how does that's all very abstract, but it's like what actually slows you down? So here I'm going to do like a quick lightning round. Okay, just to set the stage so you don't believe I'm crazy. Like this is an example paper published, and there's other ones like it by I think these are the folks from Google, where in a this 7-month period, they got, for like this, in the worst case, 2.5x in 7 months. That's equal to 8% per week on the same hardware. And I want to emphasize that, right? Some of us have designs with like around 10 cores on them, plus 8% per week is equal to getting a free core every single week on a 10-core system. Like, I mean, just think of what the hardware people would be like, they'd like, they give away their firstborn to get an extra core on that chip or whatever, right? But it's like, no, just with the right software stack, you can get plus 8% per week. And again, the this optimization is a continuous process, right? So like really, your system has to be designed to assume that the hardware is always being underutilized, because that's what lets the velocity translate to higher performance. And actually, it is true. Hardware is always being underutilized. Show me a system that is actually reaching 90% of peak, and it has no optimization opportunities for every single model that is released as it's released. Like, it doesn't exist. Okay, so let's do this lightning round here. Okay, how does this manifest? Okay, runtime. So maybe you can run your core model fast. Yeah, you can run your like llama predictor or something, but we're spending all of our time copying buffers on the host, or host device synchronization costs are taking most of our time. Or maybe we have speculative decoding, and then now performance goes completely out the window. And this one actually has a simple solution. I've tried to include some solutions here. You have to look at how GPU APIs like Vulkan work. GPUs have solved this problem for decades. You just have to do what they do. And I think just in the context of what we said, it's like, maybe your hardware can do something in principle, but like maybe you don't have the right runtime APIs to actually do that right. And it takes, to deliver it in time. Like, and so like my quick war story here is, we were painstakingly optimizing the matmuls, but then like one of us went off and saved some useless buffer copy in the host application, and then that actually was saved us a lot more end-to-end time than the matmuls. So programming, this is another discrepancy, and also to Stephen's point in the previous presentation, you need the right abstractions to do this right. So maybe you have like one critical op in your model that you have to do some like really crazy low-level thing you would never ever expect the compiler to do to get high performance, but it's like the operation, it's like taking 80% of your time. So, do you have a way to actually do that crazy low-level thing that's needed to get performance? Like, and then maybe there's like one weird op that's operating on a tensor that has like 7 elements, but because it's weird, you can't do it on your hardware, and you have to send it back to host, and then your performance goes out the window. And so the solution here is basically to expose these escape hatch programming models. And I think it's important to emphasize these programming models that let you write code in like kernel libraries rather than, munging up your compiler. Because these like, costly hacks in the compiler, usually if you can get them out into kernel libraries, then you like can scale that access. And yeah, basically, again, you're saving time because with the right programming model, you can write the right thing. So in this case, yeah, I remember I had to write a sparse softmax op, which, 10x saved 10x PCIe bandwidth, which was like a 5x performance boost for the end-to-end application. And we had to do this crazy low-level programming. Okay, profiling debugging. When things go wrong, it takes us way more time debugging it, so then we don't have as much time to optimize the model as we'd like. This resonate with anybody? And then, or maybe the model runs, but we made a number of performance improvements, but the model is still slow. Maybe you're working on performance improvements that are like 2%, 5%, 10%, but it's like 10x off in performance. So yeah, you need to have debugging profiling flows. I know that's hard because you can't always have polished tools, but at least document what you've got. Don't let those debugging profiling sessions go to waste. And yeah, like another war story, like when I wrote this better profiling tool, like we noticed like big major missing optimizations, like 30% of time doing this like one thing that we weren't able to observe well before. Then yeah, hardware ease of use. This is another one where like, has it ever happened to any of you where you're like, oh, I have my hardware, great. And then here's like a thing I want to do on it. It's like, it's a little weird, but it's not that weird. It's like I need to write a Bytonic sort for my hardware, or, I need to, write a cumulative sum or something like that. And you're like, like I know I can, like I know this algorithm, but like there's like all these details for the hardware where it's like, oh, how do I do this? And how do I do this? And how do I do this? Like it's really hard to know what's like the right way to actually implement on the hardware. And so, yeah, here, what I kind of am promoting is, keep your you can make your hardware complicated, but at least make like it regular, and modular. So like keep things connected in like a regular fashion. So it's like if I have to do my Bytonic sort or something, it's like I know it's like, oh, I need to go 2 hops here and 2 hops here or whatever. Like that's all easy to do. And again, making the compiler developers and writers of the low-level libraries more productive gives you higher achieved performance. And then, oh yeah, here's a funny one. There was this relatively mature compiler. I didn't work on this one, but it could handle a ton of models. But when a user application needed to do element-wise subtract, it took them more than 6 months to implement it. And that was, and they ended up giving up on the platform. And so that's another war story. Okay, so to conclude, basically your software optimization effort is a finite resource. And like when the hardware appears to underperform, what you'll observe at a given point in time as your hardware underperforming usually has to do with the lack of velocity in your software, which lets you get the better performance. And, if I can summarize it in one slide, is like more productive software engineers is higher performance from the same hardware. Like think about it this way, like maybe like 1 page of good documentation might actually give you 10% performance. Think about it that way. Like, it's like maybe you can get an extra core just from having a really good page of documentation. And with that being said, my shameless plug, that emoji's in a different font on this this computer, but yeah, so if I'm saying your hardware has to have a huge advantage, I happen to know one such company, which has a poster right over there, EnChargeAI, and we are hiring. So please come and talk to me or Michael, our chair, if that's interesting to you. Thank you.
Looking at time, I think we can have one short question. Yes, please.
Hi, thanks for the talk and also for bringing this very practical topic to the workshop. I highly appreciate that. So I have one comment and one question. So this is one of the bigger problems we have. My team is working on different hardware platforms, and one of the challenges is the efficiency of the hardware. We have seen numbers from 20 till 90%. And despite of all these optimizations, this discrepancy will be always there. And sometimes maybe due to the nature of the model. And typically vendors are going to blame your model, not their hardware and their tools. But this gap is still there. So, and coming to my question, another challenge we have seen is how to quantify this and let people understand this gap. Because you have multiple engineering teams that they might deliver features and models that they perform in a particular way in the hardware. And you have the leadership organizing projects in production that need to integrate multiple features. And they assume always theoretical performance. Let's say you have 10 tops, and each algorithm takes 1 top. They assume 10 will fit there in a way. But that's far from true, especially if you have 20% of efficiency. So in that case, the communication and the organization of such projects is difficult. So how do you believe this is a good metric or a good way to make people aware of this, not just engineering teams, but also the leadership organizing production programs?
Yeah, that's a really great question. And I think the answer is like, basically, yeah, once you reach a certain level of maturity in your software stack that you're scaling, like you're doing model scale out, basically, then I have actually a whole separate talk I want to give about this topic. But essentially, the idea is you want to think about having a model portfolio. So really, every time you're bringing up new models, those get included in a model portfolio, and that's what guides all the decisions you're making. And so for each model, you want to track, how long it's taking to get up and running. What is its performance when, as I was saying in the talk, what's its performance when it does work, and how long does it take you to get it to its final performance? So track those metrics for each model. I know that's a little bit of extra work, but it's very much worth it. And then additionally, across this portfolio, like when you're deciding on optimization efforts, like you have to decide like what you're optimizing. And that's where the portfolio also lets you say like, oh, well, I'm going to put more LLMs in the portfolio because I want to optimize those more or whatever. And so, yeah, I guess broadly speaking, is add those 3 metrics that I described to your model bring up process. And I think once you have like, like a spreadsheet and you can show your management, like, look, here we have 100 models. Here's like a chart showing, theoretical versus whatever. Once they have that, you can say, okay, well, we can expect 30% performance on average. By the way, if you can get 30% performance out of your hardware consistently out of the box every time, you're in a great place. So like the bar is actually not as high as you would think.
Thank you. Thank you very much. Let's thank Sean again.
Yes, I do. Will you? Yeah. Ja, wir streamen on YouTube. So, yeah. Thank you. Excellent. Thank you so much. So we are coming to the next talk. Tobias Grasser is here. He's an associate professor at the University of Cambridge, where he performs open source focused research. He co-founded the polyhedral loop optimization framework Poly, the FPL Pressburg math library for MLIR. He co-founded the LLHD EDA compiler, which later became part of LLVM, and is advocating teaching compiler design using state-of-the-art technology from the MLIR LLVM ecosystem, supported by the Python native xDSL compiler. That's pretty awesome to hear. We need the next generation of compiler engineers. Tobias was a Google PhD fellow at ENS Paris, an SNSF Ambitione fellow at ETH Zurich, and a reader at the University of Edinburgh. And he supervises several PhD students who actively contribute to open source compiler ecosystem. Welcome to Kodai Workshop.
Thank you so much. Yeah, well, thank you so much for having me. So I was thinking a little bit what I actually should talk here. So typically I try to give a inspirational speech about how AI compiler should be designed. And I thought you have a lot of experts in that space. So I actually decided to just pull out one of the very recent research projects 2 of my students did with plenty of collaborators, where, I mean, we actually at the university, we tried to build a kind of AI compiler stack ourselves. And so I had this is part of a bigger project, Convolve. It's one of these large EU projects. It's actually a hardware project where a lot of hardware people are building amazing hardware, and they kindly offered me to kind of be part of their consortium. And I was initially excited and said, that's great. We get a lot of money to do amazing research. But if you're in a large compiler consortium, you also need to deliver a software stack for the actual hardware that is built. And so obviously we wanted to get the money, and we wanted to kind of propose a great project. And so we promised to build an AI compiler stack. The problem was we had a couple of PhD students, postdocs to actually do that. And so anyone who actually built a compiler stack may have realized that might not have been the most strategically best decision to promise such a thing for an EU project. Because in the end, we also want to do some other research. But in the end, that's what we did. And so this talk a little bit about how we kind of try to deliver something that I thought would be impossible to deliver. Exactly. And so, yeah, pretty much we want to have more more performance, more compute for our AI software stack. And so one very specific example how to do that is a project from ETH Zurich, where they build a very bespoke hardware accelerator, and they replace a lot of kind of power hungry features like out of order execution, branch prediction, hardware managed caches, and scalar instructions with a lot more power efficient hardware support. So instead of out of order execution, you have something called stream registers, which automates a lot of the memory streaming. Instead of branch prediction, you actually have hardware loops. Instead of caches, you have software managed caches, and instead of scalar instructions, we have packed SIMD. And then in our Convolve project, we proposed we have one of these accelerators with many other on our SoC. And I told my PhD student, it would be good if that works. And we built some software that can make it work. So as an academic, I thought, okay, explain this student, make it work means we take a microkernel, we make it fast, we publish a paper, we move on with life. But he came from industry and he said, make it work means like PyTorch to get it running. And we had almost a year-long conversation about like what actually is the minimal viable product. And I was deeply convinced I can make the argument it needs to be kind of a subset of what's actually needed. After a year, I realized I lost my battle and he wouldn't want anything else than the complete thing. So this is Occamy. It's actually really cool as an ETH chip from Luca Benini's research group. It is cool because it is actually produced as an ASIC. So that is maybe not 2, 3, 4 nanometer, but it's I think 12 nanometer, relatively state-of-the-art ASIC. It has 384 snitch cores. It's a chiplet-based architecture, to my understanding, the first chiplet-based architecture which a handful of PhD students have produced ever worldwide, and it's cool. So we built a compiler for that. And so to understand the compiler, it's useful to understand, it has many clusters on this chip, but in individual cluster has 8 compute cores, 1 DMA core, a little bit of software managed cache. And then we have the cores. And the cores have 3 streams of, to stream your data. The streams support 4D memory accesses, and they have a multi-staged FPU. So not incredibly complicated, but also not your typical CPU, right? And so we built 2 compilers, in fact. We built one kind of neural network compiler kind of at the network level that orchestrates the entire network, organizes the data transfers. And then we built a microkernel compiler that makes sure that our microkernels are blazingly fast. Yeah, as everybody knows, I'm a compiler engineer, so LVM is the solution for any kind of compiler problem. C++ with Rust to LVMIR to the source target languages ARM, RISC-V, x86. It works perfectly well. But LVM has this well-known bottleneck, right? If your hardware happens to be a load store architecture that works on scalars or maybe vectors, LVM is the compiler to use. And MLIR showed us that for deep neural networks, we can just put the right abstractions on top, but that doesn't eliminate the backend bottleneck. So what we built as as part of our kernel compiler is we actually said, LVMIR might be an interesting target, but if you want to have full control over the backend, we want to replace it. And so we completely sidestepped LVM and just said, no, we know MLIR, it's a cool thing. Building an RISC-V assembly level dialect is not so hard. So we did exactly that. So that's this thing in the middle. But then because we are in kind of an MLIR compiler world where building abstractions is easy, we have abstractions for RISC-V level function calls, structured explicit for loops in the backend, control flow in the backend. So we built a lot of kind of domain-specific backend dialects. And then we realized, there's a lot more than RISC-V in this very particular accelerator. And because we broke open the backend bottleneck, we could just add our own abstractions. So we have more abstractions in particular for streaming and for configuration management of this particular accelerator. And so now we can target normal RISC-V core, but we can also target a RISC-V core that has very domain-specific extensions. And so just for anyone who hasn't seen MLIR or wants to get a feeling of how an MLIR backend dialect looks like, there's almost a one-to-one correspondence between any piece of MLIR backend dialect. So for example, if we have a load immediate operation that takes a constant and loads into a given register, and you can just directly lower that to the corresponding RISC-V assembly code. We can have labels. We can have an MFMA instruction, branch instructions, all these kind of things. So in the MLI community, we call such kind of dialects kind of interface dialects, right? So at that level, we really didn't innovate anywhere. I mean, I found it deeply exciting to have like assembly level model in MLIR, but in terms of the concepts of this IR, there's very little innovation, right? It's like a plain copy of the RISC-V instruction set. But we did a little bit more. So we found it quite useful to have a for loop. RISC-V doesn't have for loops, but we decided we have our own RISC-V for loop, which is a little bit of a hybrid. So it works partially on RISC-V registers and partially as a for loop construct. We have function calls that are sometimes quite useful, but in particular, for loops are actually really useful because we have hyperloops. And so ETH beforehand, they try to, I mean, they had LVM experts in their team. They enable their hardware in LVM, but these people struggle, right? Because if you have a really nice for loop and you reach the LVM backend, just looking beyond a single basic block is difficult in that backend, and kind of running a full loop analysis and recovering loop information for something that is actually just a tensor operation that has a very clear loop iteration is incredibly hard. Exactly, but you can have that very easily if your backend actually supports explicit loops. Some of you may have seen that the LVM community struggled for quite a while to get native tensor types into the IR. Imagine the struggles to kind of get native, or even worse, kind of bespoke company or hardware specific abstractions into the LVM backend, and it's relatively difficult to do that. We can do instruction selection, which are just people rewrites from a higher level MLIR dialect. So in this case, arithmetic to RISC-V. So most of them are trivial identities. Floating point operations, loads are slightly more complicated. So we have, I mean, in MLIR, we have structured memory load operations or memory access operations that they lower to slightly more complicated IR. Yeah, and then we have our kind of like accelerator specific dialect extension, which is this like hardware loop here in this case. Which gives us a nice backend. Then we get a little bit crazy. So some of you actually programmed some of these AI accelerators, realize that and that's interesting. If you want to code-generate a compiler backend for an AI accelerator, you think, oh, it's a really complicated problem. You need to kind of generate the right code. In fact, code generating for the accelerator itself is almost trivial because you pretty much just say run. And then it does all the complicated things for you, right? So where the complication is telling the thing what to run. And so it has a lot of configuration primitives that set, for example, the memory stride that you need to kind of read your data from shared memory or something like this. And so we have an entire like collection of configuration abstractions, which again, you could try to sneak into the LVM backend. It's a lot nicer if they are explicitly exposed. We have ongoing work where we're actually trying to do kind of redundancy elimination on the configuration of our accelerator. So if you kind of keep repeatedly calling the same kernels, most of the configuration really doesn't change. So if you have an explicit model of your configuration and kind of it's relatively clear like how side effectful it is or not, you really can kind of blindly emit the full configuration changes and then realize that kind of in subsequent calls to this very same kernel, you don't really need to reset up your accelerator in full, which is actually quite nice. Exactly, and then the objective is to kind of take a dense linear algebra operation, in fact, a dense linear algebra microkernel, for a single core working only in L1 memory and make it as fast as possible, right? And so here it's actually really interesting. If you look at the linear generic operation in MLIR, it has kind of to input memory references and output memory reference, and then it actually has Scala code that happens at each point in your linear generic operation. So if you would translate that to LVMIR, you would generate an explicit for loop, actually multiple of them. You would generate load and store instructions, and then you have like 10 to hundreds of operations that do whatever you want to do. In an LVM backend, then you would need to find, rediscover like 100 operations that correspond to a matrix multiply, and then you emit the right matrix multiply. with our like custom backend, that's actually really similar because we pretty much have more or less the same structure in our like domain-specific hardware extension, which also takes an input and output set, and the actual computation is RISC-V operations, which is very, very close to how the hardware works and how it needs to be programmed. And then we have a set of transformations that transform linear to this memory stream. That's what you just saw. Then we nest parameters. We optimize for the multi-stage FPU. We do some tiling, like we need to do some more transformations to do the stream operations. But pretty much the main gist is a lot of these rewrites are on a very, very high abstraction level. Like you do backend optimization at a domain-specific level, right? And that is close to impossible in like in a load store or arithmetic-based, even on LLVM-IR, even less on like pure RISC-V. And then eventually we kind of keep lowering all the way to RISC-V. Some of the optimizations is to kind of like try to pack the compute a lot more densely. So if you just load compute store, it's a lot less fast as it could be. So we kind of try to unnest some of our parameters. We interleave our operations to fully kind of take advantage of the pipeline of this compute device. We have multiple memory streams which we kind of can interleave. And so over time, everything becomes a lot more densely packed, and that gets us close to kind of the peak performance that we can achieve. We also implement register allocation. And again, one of the moments where I was slightly in, we had a lot of interesting conversation with my students because I said, we need register allocation. And they said, okay, yeah, we know register allocation. This is the thing where you optimize for spilling, right? Minimize spilling is the thing. And then they came up with like algorithms to compute lifetimes of things and figure out if they're spilling. And then I said, no, stop. Our register allocator cannot spill. Our register allocator has no spilling support at all. We want a register allocator which can't spill. And that's actually interesting because if your register allocator doesn't need to spill, it becomes so much simpler. And so obviously you don't want to spill in your high performance kernel. So the right approach if you have a high performance kernel is whenever you spill, you assert, you fail. That's the only valid response, I think, in a register allocator for like a deep learning compiler. Spilling means throwing an assertion, complaining to your like auto-tuning framework higher up that something went horribly wrong. And then our like backend dialects, when you translate them to RISC-V, they actually have here support in registers for like register allocation. And the next thing that is actually really important for this particular accelerator is that only certain registers can be streaming registers. So very specific registers can be streaming registers. So what we needed from our register allocator is to be partial, kind of incremental. We have some transformations that know particularly well how the register layout needs to be in parts for like the hardware loop, for some of the streaming registers. And then at the end, you just kind of need to do the obvious thing, kind of fill the remaining registers and hope that you don't need to spill. So we have a relatively bespoke ad hoc register allocator. It's not very complicated, but relatively unusual. And I think we would have almost no reuse in LVM from their register allocator. And so if you kind of take the baseline and then you add all the optimizations, pretty much for a very specific metric multiply a microkernel, we get up to 97% of our peak utilization. This is a very specific piece of hardware. Obviously doesn't generalize. It's a lot of like hand-coded, carefully crafted stuff, but I think it's quite nice. And I think it's an interesting artifact of, let's say, a compiler backend that is specialized for hardware acceleration of a particular microkernel versus kind of a general purpose backend. Yeah, then you can vary a little bit the sizes on which you compute. And so for anything that's not particularly extremely small, we reach very close to the like best FP utilization on that chip. So that gets us a really fast microkernel. But and I thought that this great, we can publish a paper, but then Sasha reminded me, input is PyTorch. But we kind of completed a couple of other kernels, and we're not always perfect, but we're relatively good to kind of high FPU utilization, particularly on that one matrix multiply. But kind of at that point, I said, this is amazing. But we wanted to go full PyTorch, and I thought that will not be possible. But then we were very lucky to hire one really incredibly student from the LVM MLI community, Markus Böck, who was doing a 6-month internship with us, and has done a couple of other, like, had a lot of experience in actual MLI and like working with the toolchain. So I said, why don't you do the end-to-end thing? And he said, yes, he will do it. And so then we used IREE to build an end-to-end flow around our microkernel compiler. I never know if it's pronounced IREE or IREE, but exactly. So it's called IREE. I always call it IREE for whatever reason. And this little ghost is quite phenomenal in how it can help to build deep learning compiler. It's just one of the instances of how you can build a deep learning compiler stack in MLIR, but I think it worked quite well for us. And so we have the ghost with our paired with our custom Quidditch backend. And for a little bit of plug, our custom big Quidditch backend is written in xDSL, so it's written purely in Python. It's a lot easier to prototype, but kind of we plugged it into the C++ based end-to-end compiler flow. So how does this framework look like? You take PyTorch as an input or any of the other deep learning frameworks, and then you have kind of a full compiler flow from MLIR through a couple of dialects, including this hardware abstraction layer. And kind of we added our own snitch Occamy specific hardware abstraction layer. And we have here our device code generator called Quidditch. And that all together makes a working end-to-end deep learning flow, which is amazing. We have this NSNet 2.0 as a use case, which has a couple of elementary operations that need to be run. And that's actually really nice because pretty much after passing it through the higher level transformations of that framework, we literally only get the small list of microkernels that need to run fast. And we eventually knew how to run them fast. Interestingly, I think AMD uses this compiler mostly for GPU code generation. Snitch is not a GPU, but you can program it like a GPU. It has a similar kind of memory hierarchy. It has a similar level of parallelisms. So we just assumed it's kind of a little bit of a variant of a GPU. And they are slightly different, right? Snitch has software scheduling and has a relatively small register file. But otherwise, we just need to optimize for those. And then we come up with this pipeline. So we do first tensor level optimizations, then bufferization, L1 assignment. We do a little bit of our microkernel compilation, and then we emit compute code and DMA transfer code. And yeah, that is nice. So one of the kind of interesting optimizations you can have if you're at the tensor level, you can have very explicit dependencies of your data flow, which we can model. And there's a couple of tiling that we can perform on different levels for group tiling, L1 tiling, core distribution, where we have a little abstraction here. And so pretty much we first distribute across the different clusters of this Occamy chip. And then for an individual cluster, not exactly sure what this means. I'm waiting for something that I found really exciting. But pretty much there's a lot of abstraction levels where we distribute over the clusters. And yeah, I think I skipped these ones. So, but I quickly want to tell you that anyway, I don't have that on the slides, but it's actually like Marcus came up with a really interesting optimization. So one of the main things we need to optimize on this device to kind of go from 50% to kind of full of utilization is you need to overlap kind of compute and communication. And I think I'll have later on a couple of these slides, but there was a really nice way to kind of model these things in SSA and then pretty much let MLIR just realign and how to overlap these things. But yeah, and then we do L1 tiling. Identify the reduction dimension, optimize on that level, introduce parallelism, and then we get pretty much a nesting of loop kernels that eventually run our microkernel code. We move away from tensors, So we turn them into like actual memory. And exactly, this is a slide with the double buffering. So what we have is that in the initial code, we have pretty much wait quite a long time on a DMA transfer until we can compute again. And you want to overlap that to reach kind of maximal compute performance. And so after optimization, kind of this all disappeared. And that's pretty much all in pure C++ and the MLIR level, where like at the bufferization tensor level, we do all the double buffering. Exactly, that's the example. So we have again a kind of a specialized pipeline operator, which like separates the kind of the memory copy and the compute, and will pretty much lower to perfect doubly buffered code. And then on the core itself, yeah, we distribute once more. And kind of the final performance is so the interesting thing about both Occamy and kind of the default flow of our like deep learning compiler is that by default, LVM and MLI are actually able to generate code for our chip just because it's a RISC-V CPU. So you can run on the chip without any kind of like microkernel code generator, and you get some kind of performance, which is the one you see here on the right-hand side. But if you have then a kind of a specialized code generation backend, well, then you make it a lot faster. And yeah, so we're still like, if you look at the overall execution time, then you see that this is pretty much, these are all our like microkernel code that we optimize. And then we have two more kernels. There's actually the fastest one at the beginning, which we didn't manage to optimize yet. They now take 50% of our runtime. So there's another probably 2x that we can get out of that if we would actually optimize those. And yeah, this is kind of the peak performance one could eventually reach. Yeah, and this is kind of to conclude. For me, this kind of the overall story was a very specific use case. I'm not sure any one of you is planning to build like a compiler for Quidditch, like for Occamy. But I think what is the interesting takeaway is that it is actually with the tools that we have available in the community, it's possible if you have kind of a compiler expert to build a relatively complex end-to-end deep learning stack. I mean, that actually works, right? It takes the PyTorch model, it runs on a university research device, but complex enough that it, I think, is comparable to many of the industry level AI chips. And doing that for us took, I mean, Marcus was really good and incredibly fast, so it took him 6 months to kind of set up the kind of end-to-end flow based on our microkernel generator. And the microkernel itself took probably maybe a year and a half, with like together with building the RISC-V dialects, building up xDSL as a kind of a high productivity compiler framework. And I mean, actually us kind of figuring out how the backend should be designed. But I think as a takeaway, I think it can be done. And if any one of you is ever targeting custom AI hardware, I would be really interested in having a conversation. If maybe next to the classical LVM backends, we might need another backend story. Thank you.
Thank you very much. Okay, there's immediately a question. In view of time, I would suggest we make one question only. If there's a question, of course.
Thank you so much.
Thank you for the very interesting.
Oh, hey, Joseph.
So can you hear everyone?
Yeah, excellent.
So just full word. So just one question. It was not fully clear to me. So in this compiler you are developing in the tool pipeline, are you applying for any type of ML or what optimization process is that going for? What is the
So I mean, I was a little bit rushed through this at the end, and I think the slides were not perfectly polished. But no, we don't do anything useful in the sense I mean, Marcus was really good. He kind of has a good intuition what are the right parameters for the different tiling choices, and he pretty much hard-coded whatever was needed to make things work. So there's probably another 20-30% you can get of like tuning the right, like finding the right tile sizes, adding tile size automation. I think there's some support in the IREE framework for that, but we didn't use any of that. So our objective was to get a working end-to-end prototype. We're currently like exploring if we can actually like optimize that a little bit. Thank you.
Fantastic. Thank you again.
Is Shreya already in the room? Oh yeah, fantastic. Okay, so I think we're ready set up. Fantastic. So we're coming to the last talk in this session. Unfortunately, my time management wasn't perfect, and we will need to get a bit into the lunch break. But without further ado, we have Shreya here. She's a PhD student at the University of Murcia under the supervision of Professor Alejandra Jimborean, if I pronounce correctly, and Professor Alberto Ros. And her main interests are compile time optimization and automation. And she holds masters in new computer technology from University of Murcia. And the stage is yours.
Thank you. Hi everyone. I'll be presenting my paper, Insights into Interpreters, Compilers, and Optimizers for Neural Networks. So most of the neural networks are usually trained and developed using interpreters or just-in-time compiler frameworks like PyTorch, TensorFlow, and they are usually handwritten and they are highly optimized for Intel or AMD frameworks. But when it comes to emerging hardwares like RISC-V, they are not very optimized. And adapting these handwritten kernels require a lot of significant rework. So we propose a compiler pipeline, OML, which is an extended version of ONNX MLR compiler. And we expose MLR dialects and LLVM-IR to enable automatic compiler optimizations. And with this, on RISC-V iter window core, we were able to get 2x speed up over default ONNX runtime. And so why not use PyTorch and ONNX runtime? Because they are manually fine-tuned and they use C or C++ kernels. But these kernels usually come with a Python wrapper because it is useful for end developer or neural network developers to use. And with Python wrapper, there will be a lot of library calls which add to a performance delay. And then like Python being an interpreted language offers a lot of slowdown when it is compared with statically compiled languages such as C. And importantly, they are not optimized for RISC-V CPU cores or like any other emerging hardwares. So why don't we just port PyTorch to RISC-V? Because one, we need to rewrite or manually rewrite all the optimizations specifically for CPUs, RISC-V CPUs. And there are some previous work done where they have tried porting PyTorch directly to RISC-V. Because of lack of all available libraries, there was a significant performance slowdown compared to x86, ARM, and RISC-V. So this performance slowdown comes because of two reasons. One, the hardware itself. Like if you compare Intel CPU, they are very mature compared to our RISC-V CPUs. Second is that when you check the optimizations done for Intel at compiler level, they are also very mature for Intel or AMD CPUs compared to what is currently there for RISC-V. There are also existing MLIR compiler frameworks such as Torch MLIR and IREE. But the problem is that Torch MLIR is not compatible end-to-end. That is, it just offers just-in-time compilation support and it doesn't offer standalone executable binaries. Whereas Tiny, IREE, and IREE, they are able to generate executable binaries. And they also expose MLIR dialects, but the exposed MLIR dialects like linear dialect or torch dialect, they are not compatible with upstream MLIR because of the custom utils dialect. And they don't expose LLVM-IR. Because they don't expose LLVM-IR, we will not be able to express few optimizations which are best done at LLVM-IR level. For example, like instruction reordering for better vectorization, or it may be micro-ops fusion for RISC-V CPUs. So to overcome these problems, we propose a OML compiler pipeline, extension of ONNX MLIR compiler. So we start with PyTorch, or we can start with any compiler, any neural network framework which offers support for exporting models to ONNX graph. So once you have ONNX graph, we use ONNX MLIR to generate LLVM dialect going through affine dialect. And so ONNX MLIR doesn't expose LLVM-IR, but it exposes LLVM dialect. So we use MLIR translate to generate LLVM-IR, and this LLVM-IR is our entry point to LLVM compiler. So ungenerated LLVM IR is optimized using LLVM OPT and LLVM LLC to generate assembly code. And so LLVM IR, ONNX MLIR doesn't support RISC-V out of the box. So we had to manually compile ONNX runtime libraries and then port it to RISC-V. So these compiled runtime libraries are linked with assembly code and main files to generate executable binaries. And upstream ONNX MLIR generates only shared library files, and it cannot generate standalone binaries, which is a problem for edge devices because keeping a shared library files with all the runtime libraries will be more memory consuming compared to generating standalone binaries. So we generate standalone binaries in OML compiler flow. And we also evaluated the optimizations offered by PyTorch and ONNX runtime, and we compared with what ONNX MLIR and what LLVM currently offers. And this is the pipeline that we followed. Most of the neural network models were trained using PyTorch. So we consider Python inference as our baseline. We also used PyTorch JIT for compatible models like AlexNet, but again, PyTorch JIT may give incorrect results for models, for transformer models. So we did not consider this for our final evaluation. And the exported ONNX graph were inferred using ONNX runtime. And we also generated executable binaries using OML compiler pipeline. The main optimizations offered by PyTorch are the vector extension specifically targeted for Intel libraries using MKL DNN library. And they also perform fusion of unary operators like fusing ReLU with the next immediate map attribute function. And there are also some binary operation fusions like convolution will be fused with the next activation function, or it can be a bias addition function. With all those optimizations, ORT builds on the optimizations offered by PyTorch, plus it also does some graph optimizations like fusing multiple nodes into single node or statically computing all constants. And it also partitions the graphs into subgraphs. So like a subgraph will be executed using a dedicated execution provider, for example, one DNN specifically designed for Intel CPUs. And so at ONNX runtime, optimizations are done like before the partitioning of the graph, plus once the graph has been partitioned. One example for a subgraph optimization is convolution and activation fusion for CPU execution provider. So we tested 10 pre-trained neural network models, and they're so out of which like 5 were classic convolution networks like AlexNet, MobileNet. And we considered one RNN model, that is NSNet2. And we had 2 dynamic models, that is variations of NSNet2, dynamic layer-wise and dynamic simultaneous with extra layers. And we had 2 transformer models, one is Googlebert, other one is Roberta. So all these neural networks were verified on x86 CPU and on a RISC-V core as well. So we evaluated correctness of all the models, and we found that relative and absolute error was less than 10⁻³ for most of the models. And on x86, we evaluated using PyTorch, ONNX runtime default or open source version, and our pipeline. And on RISC-V core, we evaluated using ORT, ONNX runtime with dedicated execution provider, Semidynamics, and OML pipeline. So we compared the speedup of PyTorch on x86 CPU, and we compared it with ONNX runtime default and OML. As I mentioned before, because the models were trained using PyTorch, we considered PyTorch performance as our baseline. And all the results are actually normalized for PyTorch runtime. We can see that ONNX runtime is performing much better compared to PyTorch for most of the models. That is because of the optimizations offered. One example is that, so in ONNX runtime, they perform a lot of loop unrolling and loop fusion, which has given more performance with respect to vectorization, whereas PyTorch does template-driven loop unrolling, which is not very efficient compared to the hard-coded loop unrolling that is done at ONNX runtime. And we have OML results. So OML is not performing very good compared to PyTorch or ONNX runtime for x86. Reason for that is OML is single-threaded, whereas PyTorch and ORT by default, they are multi-threaded, and we had 12 cores on our CPU. We did not attempt to build PyTorch and ONNX runtime single-threaded because our aim is to improve the performance of OML. So we wanted to still evaluate for the 12 cores itself. And then we present our results for on RISC-V CPUs. And because PyTorch, so because all the libraries are not available for PyTorch to run it on RISC-V, PyTorch was not considered for this results. And here ONNX runtime default or the open source version was our baseline. And all the results are actually normalized for ONNX runtime. So when we compared the performance of ONNX runtime with OML pipeline, for classical models, we noticed that for AlexNet, OML is not very good when it comes to performance. But as we see, like for MobileNet and ResNet, OML or the automatic compiler optimizations are giving more performance. But the other side of the story is that because they are very old, or the convolution or conventional models, so ORT default has a time for the developers to manually write all the optimizations for RISC-V or to port all these optimizations for RISC-V. But when we check the results for NSNet2 or Google BERT, which are new models and more complex models, we can clearly see that automatic optimizations offer better performance over the manually written ORT, because it is very difficult to rewrite all these optimizations manually, and it is very difficult to keep up with the emerging phase of hardware and also the evolving neural networks. So we were able to get average 2x better performance using OML compiler pipeline compared to ORT default. Again, we also evaluated this on the same CPU core with semi-dynamics execution provider. And so we can see that semi-dynamics execution provider speed up is very high compared to OML. That is because this execution provider is specifically optimized for the given hardware, and it contains manually fine-tuned libraries. Our aim is to increase the performance of LLVM and bring in all the optimizations offered by semi-dynamics execution provider into LLVM, but in an automatic way, so we can reduce manual rewriting of optimizations as much as possible. And then we have a case study on NSNet2. So we wanted to consider a more complex neural network, RNN model with dynamic variations, and then like do a case study on it, what ORT default offers and what LLVM offers and what LLVM compiler currently lacks for neural networks. And why did we choose NSNet2? That is because, so this is a use case designed specifically to run on edge device. And it was developed for real-time denoising, and we were able, and it's a more complex neural network compared to convolution neural networks. And we have 3 versions of the same neural network, so we can compare the performance. So we studied 3 versions of NSNet2. One is a baseline version, which contains FC fully connected layer and GRU, that is gated recurrent units. And so for NSNet2 dynamic layer wise, there is an early exit stage after each fully connected layer. And for the 3rd version, that is dynamic simultaneous layer, so the architecture is very similar to dynamic layer wise, but it also contains an extra or duplicate layers of all fully connected and GRU layers. We evaluated NSNet2 on PyTorch on x86 platform, and we found out that for baseline, there were 30 threads created, and for dynamic layer-wise and simultaneous, there were 35 threads created. Unfortunately, due to lack of available libraries and profilers, NSNet2 was not profiled on RISC-V CPUs, but we analyzed the optimizations offered by ORT default, and we notice that the computationally intensive layer was GRU, gated recurrent unit layer, and which can further be broken down into jump layer tanh activation with some loop for bias addition and like other function calls. So in ORT default or the open source version, only jump function was optimized for RISC-V, whereas the tanh and like other loops were not at all optimized. That is the reason why OML or the LLVM autocompiler optimization performed much better compared to the default ONNX runtime. And it is very challenging to manually incorporate all these optimizations into emerging hardwares. So with MLIR and LLVM frameworks, we will be able to automate most of these optimizations, and it can be extended for future hardware changes and also for upcoming neural network layers or neural network kernels. So when we checked NSNet2 with respect to LLVM, like we noticed that there were 37 loops which were considered for vectorization, whereas only 11 loops were vectorized in LLVM. That is because unsafe floating point operations, scalar cost being the optimal cost, and unvectorizable types such as function calls inside a for loop. So we believe that with loop fusion, partial loop unrolling, and then like combined with other optimizations at MLIR and LLVM level, we will be able to match the performance of manually fine-tuned execution provider automatically using OML pipeline. Yeah, thank you. Thanks.
Thank you very much. There's some more questions actually. Any questions from the audience? Camera. Oh.
So my understanding is that most of the low-level optimization that you're doing now.
Yes, so we are doing few optimizations at MLIR level, but we are also doing most of the optimizations at LLVM.
I'm curious what you personally think about Tobias' talk, and whether it would be more interesting or performant to do those optimizations at the MLIR.
Like the microkernel compilation and OML pipeline, it was actually developed under the same Convolve umbrella. So we wanted to target like both the sides. Like one is specific hardware optimizations. Like that's why we have xDSL flow, like that was developed by Cambridge. And we also wanted to target the general purpose CPUs, and that is where LLVM or like OML pipeline will come into picture. Like because using LLVM, we can target more general purpose CPUs and we will still be able to get more performance compared to manually fine-tuned. But if you have a specific target hardware, like which you know the requirements, then you can definitely take xDSL approach and you can get more performance.
Any other questions from the audience? That's not the case. I would have one last question. I think very much in the beginning of your talk, you stated that you leverage the execution providers for deploying to various devices, and that you also split the model into various subgraphs.
Yes.
Can you comment maybe a bit how you split the models, and if you use a heuristic, or is there a manual input for how to split the models and to dissect them onto different execution providers?
So it's actually done by ONNX runtime libraries, and they sort of manually do it. For example, so if a jump kernel is optimized for semi-dynamics hardware, which is our test case, so ONNX graph, like it is going to search whether the operator is implemented in execution provider or not. If it is implemented in an execution provider, then the graph will split accordingly and it will run the execution provider code. If it is not, then it will fall back to the default flow that is open source version. So it's done at ONNX runtime library.
Thank you very much. If there's no further questions, then let's thank Shreya again.
Okay, this brings us well in time. Wow, to the minute for the lunch break. I think we will be back at 2 p.m. For those of you who noticed, it's rather cold in here. I noticed myself, I'm still wearing the scarf. We asked to increase the temperature for the afternoon. I think that's already happening. And anyhow, I think the topics also this afternoon will be super hot. So please come back. Also, there will be a Best Paper Award being announced at the very end of the workshop. So for those of you very interested in that, please stay tuned. See you later. Machst du das Pause-Ding drauf?
Some days, you know, I don't want to get very.
Okay. So maybe we can start. Welcome to the second session of CODAI. My name is Miguel Ángel Aguilar. I am a manager and senior expert for embedded AI at Aptiv. It's my pleasure to introduce you the speakers today, particularly because we have the presence and participation of former and current members of the IC Institute at the WTH University, led by Professor Leupers. And we will start with Andreas Bytyn, who received the master and the PhD from the RWTH University in 2014 and 20. Before joining Axelera AI in 2022, he worked as assistant architect and team lead within the automotive division of Bosch. Then in his current role as director of compiling engineer, he is responsible for the development of compiler toolchains for the Axelera in-memory compute-based AI accelerator. So he's going to talk about the anatomy of an AI compiler. The stage is yours. Thank you.
Thank you very much, Miguel. Set my timer first. All right, good afternoon, everyone. So around half a year ago, Michael asked me if I would like to give an invited talk to CODAI. So obviously I said yes, for sure I want to do that. Now coming New Year, I remembered I have to give a talk. And I thought, you know, at that point in time, you know, like all the patents would be filed, all the papers written, so I can talk about the very guts and like this super cool technology in the Axelera compiler. Obviously, they are not all written and not all filed. So I went back to the time when I was a PhD student and I thought about like, what could I talk about that people would be interested in, right? And since this is a forum where both industry and research come together, I thought it would be kind of nice just to hear about, you know, maybe a company who has developed an in-house accelerator and who also has developed a compiler for that, and maybe get a bit of a digest on how that worked out, you know, like the different parts of it, maybe at a high to medium high level. And that's exactly what I'm going to do today. I hope there will be some questions in the end. And let me start by giving you a brief overview of the content today. So firstly, I want to very briefly introduce my company, because after all, they're paying for both me and my colleague Matthew, who's somewhere in the audience here, or maybe not yet, to come here. Then I'm going to give you a brief overview of the hardware architecture that you can actually buy as of today. So that's hardware that's on the market today. The Metis AI processing unit, I'm going to give you a very brief overview of the software stack. And then obviously I'm going to go into the compilation pipeline that we have for said accelerator. I'm going to give you some very brief statistics on the code base that I found somewhat interesting. And I'm going to have one slide about lessons learned. Thank you, Sean. I'm going to refer to you a couple of times, I think, now throughout my talk, because I saw a lot of similarities and that was really, really interesting. I might pick up on that in my lessons learned slide. All right, so XLR AI. I think that's to date the largest European AI semiconductor startup. We were founded in July 2021. To date, we have roughly 120 million in funding, about 200 people working for the company from 15 companies. We have some offices in Eindhoven, Zurich, Leuven, Bristol, but also a lot of people working remotely. Actually, most of my team works remotely from different locations across Europe. What I find really remarkable is that we have around 1/3 of all people holding a PhD, a lot of them from renowned European universities. So that makes for a really good team. And actually, frankly speaking, it's a lot of fun working at Axelera and specifically working in this really fast-paced kind of domain. So I'm not going to talk about how great we are, because if I look at the EnChargeAI poster over there, apparently when it comes to energy efficiency, we are doing pretty poor. So I might get back on that, talking to Michael and Sean afterwards. Yeah, and I mean, team, that's an important keyword. So everything I'm showing here, I mean, that's obviously teamwork. We have a really great team. We also like to have fun. I think that was in Kitzbühel 2 years ago at a company kickoff. We've actually been to Barcelona last year, May. I didn't have any pictures for that, but I think it's really important to notice that anything I'm showing here, that's all work done by the team, not just by me. So thanks a lot to everyone involved. All right, let me talk about what Axelera's mission is. So we say we want to democratize AI. What does it mean? So we want to make AI available to all players, big and small, at reasonable cost. Obviously, now, if you want to have just the highest performing solution, you'll probably end up buying an NVIDIA GPU for 50K or something, right? But a lot of customers, they're not looking just for highest performance, but what they're looking for is actually performance per dollar. And that's what customers are asking for. Now, in order to achieve that, we also want to achieve, obviously, a high energy efficiency, but not because somebody, like some customer, really cares about how much energy or how much power actually an edge server consumes, like let it be 30, 50, 60 watts, like they don't really care. Like what they care about actually is to get in as much compute power as possible into a small form factor, such as M.2, which might be passively cooled, or in general, you know, like if you have a small system, I mean, you have usually your cooling limited. You want to have high accuracy for your workloads. So that means you need to have good quantization and ease of use, which is where the compiler comes into play, right? For most customers, model retraining is not an option. So you need to go with post-training quantization. This is why we choose to use int8 for both weights and activations, but we have full precision accumulation in our hardware unit. There's also some floating point in there. I'll come to that in a little bit. And flexibility is key. So we're using different RISC-V controllers in our hardware architecture, mainly to steer the control flow, to orchestrate execution, at least in the current hardware generation. Let's put it this way. All right, so let's talk about Metis. Like I said, that's the first actual product that we brought to the market. We have customers using that today. That's why I can also talk about this quite freely. The architecture, it's a 4-core architecture with 4 AI cores. Each AI core has a digital in-memory compute array. It's basically a matrix vector multiplier that can deliver up to 52 TOPS peak performance. The IMC array itself, it can store up to 1 megabyte of weights. We have 4 megabyte of L1 software managed scratchpad memory. Attached to that, the RISC-V controller to orchestrate the data flow. And there are also units such as the DPU and the DWPU used for vector processing. If you want to do like activation functions, quantization, or the DWPU for depth-wise operations. There's also an LPDDR4X interface so that we can attach DDR memory to it, and a PCIe interface so you can communicate with the host, because we're not just selling the accelerator on its own, but we're actually selling complete systems. So you also have a host, and there's also part of the software running on the host so that you can set up the complete pipeline. All right. A few brief words on our software SDK, which is called Voyager. So I guess some people at Axelera really like Star Trek. I for sure do. Watched every episode. So we have 2 different environments, the development and the runtime environment. Now, obviously, as part of the development environment, we have the neural network compiler, with also different profiling tools, debugging tools, and this AI pipeline builder, which allows you to stitch together not just the neural network, but also other parts. If you want to feed in a camera feed, you need to do some pre-processing, post-processing, business logic, all that sort of stuff that you need to implement as a customer. And if you want to set up an end-to-end solution, you know, feeding in multiple camera streams, doing something with that, and then actually getting a tangible result. In the runtime environment, we have the Axelera runtime, which implements Intel's One API. More specifically, we implement level 0, which is the lowest level part of One API, to manage the communication between the device and the host, which is super useful, actually. And obviously, there are drivers for the PCIe. There's also a software part that's not shown here, which is the firmware and runtime on the chip, which is huge. And if you want to get to the best possible performance, obviously, specifically the runtime on the chip, that's super important. But I cannot talk about that today because that would completely blow the time frame that I have. So let's rather talk about compilation. Now, if you are coming from the compiler domain, which I'm assuming, I mean, this is not a big surprise to anyone here. So we have, I mean, maybe first of all, yes, our compiler is TVM-based, not MLIR-based. I'm happy to discuss that afterwards. So the toolchain overall, I mean, we have different model inputs formats that we support, like Onyx, PyTorch, TensorFlow. And nobody uses TensorFlow these days. If you do, I would suggest you stop doing that. Most customers actually give you an Onyx model or maybe PyTorch model. I mean, just my experience. We have a quantizer written in PyTorch. So that's a custom quantizer that on its own, I think, would deserve a complete talk. But I'm just going to leave it as a box here. So what we get out of that is a torch script graph that's then imported to TVM's first level IR relay. We are reusing parts of the PyTorch front end that TVM already gives you from the get-go, but this is heavily modified, so it can cope with everything that the quantizer can basically give you. And then at each different representational level, obviously, you have a set of transforms. So we start with the front end, then we have conversion steps between the different representational levels, going to the mid end, going to the back end. For the back end, we are using TVM's own Tensor IR. I think that's probably somewhat similar to MLIR, LinArc, or affine dialects. I mean, experts here, you tell me. And then when we leave the TVM world, we go into something called ATEX. That's specific. I'm having one slide on that. That's basically a hardware-specific representation for all the different hardware units in our architecture. And out of that, we can generate code for the RISC-V controller and then link that against the runtime and everything. So you get an ELF binary that will allow you to execute that network efficiently. All right. So let's talk about the front end. The level of representation in the front end is at the neural network operator level, right? And I picked a simple unit test here for convolution, so nothing too fancy. So you see you have like a convolution, then there's already some Axelera specific part in here, like the rounding to float 18, specific data format we have in our vector processing units, and some other stuff in there. And the main objectives that we want to achieve at this representation level are, first of all, we want to rewrite operators such that they match our hardware as best as possible. This usually means that we want to harmonize the layout, for example. You have some frameworks providing you workloads with channel last or channel first layout. So you want to ensure that this is completely harmonized across your entire graph. Then very important, we want to ensure data alignment. So the hardware architecture in itself, that's aligned to 512 bits. So if you are going with int8, that means 64 element alignment. And you, trust me, you want to make sure that you achieve this alignment as early as possible in the flow, or it's going to bite you on the back later on. So we're doing everything we can to already ensure alignment at this level here. Then there are some optimizations like simplification of operators, Foley constants, all that sort of stuff, and the graph partitioning to see what we can and cannot offload to the accelerator. Coming back to Sean's talk, actually, like if you have to offload something in your graph, that's going to completely destroy your performance. So we try to avoid that at all costs. And usually it's just some parts in the beginning or the end of the network where you say consciously, okay, like this is actually better executed on the host for X and Y reasons. But you still want to be able to do that sort of partitioning here. Then we come to the mid-end. That's still in TVM's relay IR. I think that's probably a bit of a hack, you could say. So if you were living in MLIR land, you probably have written your own dialect for this. So we had to basically get this in a bit contrived. So now we're going away from these high-level descriptions of operators towards something that maps more closely to our hardware. So you see, for example, you have these stream in operator, stream out, an MVM operator, DPU element-wise, etc. So that's still fairly agnostic in the sense that we know nothing about memory planning, scheduling, all that sort of stuff. Like you're basically clueless here at this point, but you already know how these individual operators break down to your individual hardware units that you have available on your chip. Things that we do at this level are, for example, fusion of operators. If you have multiple operators on your vector processing unit, you can fuse them together. Or if you have patterns like stream out, stream in, then you can probably just, merge them together and avoid going back to memory. Also, for some operators, you want to insert bypasses into hardware units because our hardware is a stream-based architecture. So even though you might just want to do something with the vector unit, you have to go through the MVM. So you need to insert the appropriate bypasses. Coming to the backend. So now we have quite different representation. Like I said, we're using TensorIR, TVM's TensorIR. Now pretty much all computations and data dependencies are very explicitly written down in the IR. And like even for the simple example of a convolution, I couldn't give you the whole IR. So I just picked two pieces here. You see, for example, if you have a DMA transaction, I think that's presumably for getting the weights into L1. You have a constant allocated in L2. You got another buffer allocated in L1. Then you have a block with hardware unit annotated for the DMA. And you have a buffer store statement inside. So later on, when you go through the backend, you'll be able to identify which data to load from where to where. And you can also extract some patterns if you need that. So if you need to do a multidimensional DMA, for example. Same goes for the DPU operations. I mean, this is actually much simpler. You see, we have a multiply addition still in there. And the hardware unit is now obviously the DPU instead. And that's pretty much the representational level in the backend. Now, the main objectives, what we want to achieve in the backend are, first of all, very important tiling of operators. So especially for large networks, you will not be able to fit the feature maps in the L1 memory. So you apply tiling, you make them smaller. You want to apply some low-level operator fusion, for example, depth first processing, so that you avoid going back and forth between memories as much as possible. Then very importantly, asynchronous scheduling. So we introduce software pipelining in the first stage, and then we do asynchronous scheduling so that you have both compute and memory transactions in parallel as much as possible. Let's say you compute one layer, you will already want to prefetch the weights for the next layer or maybe the next tile, stuff like that. Then there's a bunch of optimizations to maximize the IMC utilization. I have one slide, maybe at the high level, illustrating what the problem is. So there are some things you need to do at the lowest level in order to ensure that you have a decently good utilization of your in-memory compute array. And maybe one of the most important things being done in the backend is actually the memory planning. So in my and my team's experience, that's oftentimes actually like the deciding factor in performance. Like that's do or die. Like if you do good in terms of memory planning, you will achieve your performance numbers, especially for large workloads. If you don't, you'll end up stranded at some performance ceiling or supposed ceiling that you cannot exceed. Okay, let's briefly talk about ATEX. That's the AI Core Task Exchange format. It's a JSON representation, which for each hardware unit at each point in time basically gives at a register level, so bits and bytes, the description of what these hardware units should be doing, how they should be programmed. So think of it like the instruction set architecture, maybe the assembler of the hardware architecture. There are also synchronization tasks in there. We have both hardware and software synchronization, but again, not enough time to talk about the synchronization model in detail here. Now, the main intent, like I said, is to capture the register level transformation representation, but also to have an easily interchangeable format between different tools. So this goes into the code gen as we've seen before, but we also have performance simulators, we have debugging tools, profiling tools, all that sort of stuff. So you want to have a unified format for that. And this is what ATEX is for us. There are also some static checks we can perform, for example, to detect some out of bound values if the compiler did something wrong, which obviously never happens. So this gives you an additional level of security. All right, so let's briefly talk about IMC mapping. I've mentioned we have a digital in-memory compute array. That means we have actually a data parallel dimension. So anything happening across that dimension happens in parallel, and there's a sum reduction dimension. So yeah, just like you would expect a matrix vector multiplication to happen, right? So you do multiplies, you sum them up, you get values coming out at the bottom. Now, since I said we're talking about vision, I'm also coming to you with a vision example, which is a convolution. So sorry, no attention layer here. This is a simple convolution example with a 3x3 convolution, 128 input channels, 192 output channels. So if you write down your filter kernel with nice colors here, you basically end up having these different filter kernels. And anyone who has worked with any kind of matrix multiplier before knows that the thing you want to do in order to compute that convolution is an im to call transformation. So what that means is you take each kernel along its reduction axis, you build basically a column vector out of that, you stack the different column vectors next to each other, and then you end up with these vectors down here, and you actually encounter one issue, which is if your reduction axis exceeds the length of the reduction axis on the array, which of course is limited in hardware, well, what are you going to do then? You're going to start slice across the reduction axis. So instead of just having one nice parallel reduction rectangle on your array, you end up having multiple of these rectangles on your array. And then you start doing what we like to call the Tetris game. So you try to find an optimal mapping of these different rectangles onto your array, both minimizing or ideally completely avoiding any sort of fragmentation, because obviously you don't want to waste any space on your array. And at the same point in time, you want to maximize somehow the utilization of the array. But this is a naive mapping, which is pretty bad actually, because at any point in time, only one of the rectangles will be active. And let's say it's rectangle 2, I think that's only 1/16 of the array. So that makes for a pretty poor utilization. Now, I'm not going to show you the solution, unfortunately, because I'm limited on time, but there are transformations you can do, like replicating kernels, doing dense packing of inputs and outputs, and some clever mapping optimizations onto the array that actually allow you to increase the utilization in the array. You always have to weigh that against the overhead that comes with that, meaning more overhead to program the array, more overhead because the weights, for example, will grow in size, that sort of stuff. So we have heuristics in the compiler which estimate all of these different impacts and then pick a best solution based on these heuristics. Now let me briefly talk about memory planning as well. I said that's often actually do or die, especially for large workloads. Now, in our case, we have a multi-level memory hierarchy, so at least L1, L2, and DDR, and you might even want to consider the IMC itself one additional level of memory hierarchy. Now, the objective that you want to achieve during memory planning is you want to find, at least in our case, we're doing static memory planning. I should have started with that. So no dynamic allocation as you would have, let's say, on a GPU or so. So we completely statically plan the memory layout at compilation time. So you want to find static allocations such that you keep all data as local as possible, so keep it in the closest memory to the compute units. And you want to reduce fragmentation as well, because fragmentation, that's the evil in memory planning. Sometimes you have just a very small tensor lying around, which completely blocks the space from being able to be occupied by larger tensors. And I asked one of my colleagues to give me one of these nice plots that we have. That's one of the debugging tools you definitely want to have in your compiler if you do that sort of optimization. So you have DDR, L2, L1. On the x-axis, you basically have your time in the network. On the y-axis, you have the memory utilization, so how much memory the buffer takes up. And the ideal outcome would be that I don't see a single spot of white anymore here. So everything is all used by buffers, like there's no white left. Obviously, you're not going to achieve that in practice, but you want to come as close to that as possible. And this is actually quite good, I would say, from previous experience, because I know how this looks if you don't apply some certain optimizations. And the large challenge that you're encountering during memory planning is actually that memory planning is super codependent on other optimizations that you perform. This is actually the whole story from 40 years ago, like between register allocation and instruction scheduling. Now you have the same thing here because you also have a scheduling component and you have an allocation component, and there's a lot of codependencies. So the tiling, obviously, if you do tiling, the buffer sizes are going to change. That's going to alter your memory plan. The scheduling itself, that's going to influence the lifetime of buffers. So if you decide in the scheduler to bring in a certain buffer sooner, that means you have like a larger consumption over time, which might block certain spaces in memory from being used well by other buffers. And there are also specific optimizations like compression of constants, also folding of weights into the IMC array, which will most often actually influence the lifetime of buffers and therefore have somewhat of an impact on the memory planning. So how do we solve this? Well, we don't have the golden solution that does it all perfect in one go, but instead we do what I think everyone does. So we have an iterative approach where we have some heuristics. So in the first go, you have some heuristics, some analytical things that you can do to calculate some things you can do some explorative lowering. And based on that, we do a first memory plan. You see how well that turns out. Maybe you're lucky and it's good already. So then congratulations. And if it's not, you try to use directed feedback and do the memory planning again, for example, doing some more tiling or similar. All right. Few statistics of the code base that I found somewhat interesting to share. I was actually a bit surprised myself because I calculated these numbers, I think, last week. So I brought you this plot here where you see on the different bars are for the different representational levels. And we have the yellow bar showing you the relative number of passes that we have at the different representational levels. And the gray bar shows you how many lines of code are in these different representational levels. Now, roughly 2/3 of all passes that we have are backend related, which is not a super huge surprise, but still it's interesting to see that in numbers. We have around 100 custom compiler passes that we had to write on top of what TVM was already giving us. And writing backend passes seems to be somewhat more code intensive than writing front-end passes, because you see this gray bar here, it's actually exceeding the yellow bar, whereas for front-end and mid-end, they're actually smaller. This also coincides quite well, I would say, with my personal experience that oftentimes writing something for the backend just takes more time than doing a front-end transformation where you, I don't know, like fold some constants into some operator. Now, the unfortunate truth is that, I mean, especially the backend, that's super hardware specific. So, and that's my personal opinion, but the gain that you can get from using a particular framework or, yeah, I mean, that's really limited because you're going to be writing very specific passes dialed very specifically to your hardware. And that's what you see here, like the most of the effort actually is going into that part. And I'd be more than happy to give up some of the front-end passes to some magic framework that does them all for me. So if you know one, please let me know. I'm happy to talk to you. All right, so last slide, a few lessons learned. So disclaimer, these are subjective lessons learned by me and my team, and this is pertaining mostly to vision workloads, okay? Maybe next year I come back and talk about LLMs, but for this talk, it's about vision workloads. Now, first one is getting the basics right matters much more than implementing advanced methods. So from personal experience, I can say if you just implement all the basics the right way, you're probably at 80–90% of the achievable performance, so you don't have to reinvent the wheel. We did, in fact, implement some rather advanced methods, specifically when it comes to multi-core scheduling. I didn't talk about the topic at all, but there are different ways that you can schedule workloads on a multi-core system, right? You can do a batched execution, pipeline multi-core, you can do hybrids of that. And for some workloads, this will actually give you a quite substantial gain in theory, but often in practice, I mean, a lot of the difficulties of implementing this in a way that it can actually be used for any kind of workload by any customer that's going to diminish your gains. So you're doing very well implementing the basics right first. A second point, I already touched on that. Again, my personal opinion, but there's no right or wrong framework for your compiler. You'll end up writing a whole lot of stuff yourself anyways. So again, just my 2 cents. Then this third one, I think that's more universal, fast development cycles and easy interactive debugging if possible. That's key. That's also one of the reasons why I personally and my team really like TVM. It's a lot of Python based. Yes, that's not super fast, but it means you can super easily debug stuff or change stuff as you go, which has been super helpful in building up this compiler in a rather short time. And last but not least, no simulator beats having actual silicon. So I come back to Sean, your slides. It was really insightful, you know, where you said like this first out of the box performance and then getting up from there. So from my experience now, having gone through multiple bring-ups of multiple chip generations, actually, this first out-of-the-box performance, you might be able to get like an okay out-of-the-box performance using some simulators that you have. Still, it won't work the first time that you try something, but it will drastically cut down the time from getting silicon to getting something to run. But then extracting like all of the possible performance, you really need silicon for that. There are so many dirt effects in there, things that you didn't expect, also things that other teams do, not out of bad intent, but there's a runtime component, there's a host system running, there's a lot of stuff going on that you cannot possibly capture in a simulator. So you need actual silicon if you want to get full performance, and this has been key for us. All right, thanks a lot. I think that concludes my half hour.
So do we have questions?
Hi. Very clear and nice talk. So my question is regarding power and energy, because you started with the presentation that the whole solutions oriented for power and energy efficiency. When we will see a compiler toolchain after it compiles things, okay? So all the optimization, I guess, now you have done are regarding the run time, right? So how fast is it? When can we see a compiler output a power and energy number at the end? So after compile. And the second question is, how many of those optimization passes that you had on your slide regarding power?
Okay, so I mean, the first one is a quite general question, right? I cannot tell you when the compiler word is going to give you these power numbers as part of the compilation step. I know we have tooling internally, I can tell you, to give you that a little bit, but I mean, that always needs to be calibrated to the silicon that you get. And I mean, there's always some accuracy offset that you have. So honestly, I cannot tell you when everyone is going to have that available. The second question I might be able to answer a bit more in detail. So there are, I mean, for our hardware architecture specifically, the power, I mean, it's dominated by the IMC array, right? So you can calculate how much average activation you have in the area, and that's going to correlate pretty much straight on with your power consumption. And we are having mapping strategies that allow you to, let's say, either actively choose for having the maximum array utilization, or for saying, okay, I might want to take into to be okay with having a smaller array utilization at some point in time to reduce the peak power that the hardware architecture might consume at the cost of potentially sacrificing some performance. So we do have some trade-offs that can be made in the compiler, and that's all in the IMC actually, because like I said, I mean, this is the huge power consumer. Yeah.
Last question. I was surprised you have these 100 compiler passes in the backend, which is terrible complexity. In my normal compiler construction, there's a space ordering problem. So how do you make sure you actually bring all the space to the right order, or to the order? Yes, it's a natural language, it's a scripting language.
Well, we don't have a specific description language. I mean, the setting together like the pipelines for the passes, I mean, that's done in Python, right? So, I mean, it's just code that you write and you decide actively like which transformation passes to run in which order. And I do agree with you, like there is an ordering issue that you have, specifically, again, coming back to memory planning, because if you decide to run an optimization before or after memory planning, it's going to have profound impacts on how your buffers are modified. So I'm going to be honest with you right now. I mean, there's a set order that we know works well. So I wouldn't suggest that you start reordering that at will. We always try to do our best to make these passes as general as possible. But I think in the end, yeah, I haven't come up with a final solution to that yet. Yeah, it's a good point.
Move to the next talk.
Thank you.
Fine.
Yes, it's me.
Oh, it's sehr good. Good. All right, I think already on.
Young. So our next speaker is Young Maurice Joseph. He's the co-founder and CEO of Roofline. Previously, he held various roles in research with focus on computer architectures and AI. Dr. Joseph received multiple awards, including HighPeak Technology Transfer Award and the Faculty Award for his PhD. Furthermore, he is a member of the Young Academy of Arts and Sciences in North Rhine-Westphalia. Looking forward to learn about Roofline.
Thank you. Yeah, thanks everyone, and welcome. Thank Miguel, and welcome everyone to my presentation. So after the most successful hardware startup in Europe, I hope this will be at some point the most successful compiler startup in Europe. So it's a pleasure to, no offense to you, it's a pleasure to be able to present what we are doing at Roofline today. And our mission is to make AI deployment at the edge simple, because we feel that there is an urgent need for a flexible deployment solution that is able to be retargeted between GPUs, CPUs, and neural processing units. And yeah, as Andreas just said, basically tackling this problem of having a more unified front end that you can just use for your specific hardware that you are looking into. So why are we doing this? And I hope this is something most of you already know a bit, because you are in the space. We are trying to tackling the problem that the deployment solution that we have at hand are slower evolving than the actual AI models out there. So people are constantly innovating in terms of new models that come to the market, and we as compiler engineers have to support this. And that's kind of a tricky problem to tackle. And on the other hand, if you take a look at the hardware that is out there, especially in the edge AI market, it's getting more and more complex. It's getting more heterogeneous. And so basically, nobody really wonders that you need 100 passes to compile for a specific target, because if you take a look at what's out there, it's just to meet the performance and power efficiency requirements that we have, that's a huge beast to tackle. And this all in a space where, performance is imperative. And so we really need solutions for this to make the deployment process at the edge a less painful thing to do for everyone. And this is where Roofline comes in. And this is also basically our mission statement here. So really to enable any chip that's out there to efficiently run any customer model. And this would, if you think about it from a vision, it would really enable customers with their AI models to really bring them to edge AI devices, select the device that solves their problem, and by this really expanding the reach that AI has in the edge AI space currently. And so basically, what does that mean? That means our software development kit is in between what the customer does with the AI model and then the chip that you might be providing to the customer. And the SDK of us really gives you this flexibility of different AI models and different targets that you can address here. We are really looking into efficiency, thinking about latency and memory footprint mainly. And we also are looking a lot into how to make this process easy to approach, and thinking about the usability from a ML developer perspective. And with these three values, I think what we would enable is to make AI deployment much easier. And this is essentially what we want to achieve. So going from this very high level a little bit lower, what does it specifically mean here? And the first thing that I would like to look at today is flexibility. And for us, flexibility, as I said, is a two-sided game. It's on the one hand side, really looking into different AI models and understanding what the customers want to deploy and supporting this, also basically coverage in that regard. And then on the other hand, looking into different target hardware that you want to support because people are using them in the market. So at today's stage, where are we at? So yeah, we support any framework, TensorFlow, PyTorch, EarnNX, and Yax. And of course, you shouldn't use TensorFlow, but people still do, unfortunately. So yes, we do have an importer for that as well. And then from a model perspective, we have an internal model zoo that is covering conventional AI models, so vision tasks, for instance, CNNs, RNNs, but we are also always monitoring what's out there on Hugging Face to also cover any like modern transformer-based architecture and really be up to speed with what the end user is really employing in their products. We have then built basically a two-piece product out of this. So number one is Attic. Attic is our AI application layer. It's if you want the front end to read in your AI model and then bring it down to an abstraction so that you can target your specific hardware that you're looking into. And then on the other hand goes Seller, and Seller is then the specific component for one of those targets that you're addressing. And on the target side, we have in-house pipelines for ARM, x86, RISC-V, typical GPUs that you find on the market, as well as SPIR-V and NVIDIA currently with a lot of focus on there. And we are also looking into how to address it to specific AI accelerators for NPUs to also have the interfaces ready there and address this. And if you think about it, how can we achieve that as a small company, but also give a value to basically to the larger community that is really wanting to bring these AI models to their chips? And I think the only solution is to basically build on a scalable open source technology so that some parts are out there, and then specific proprietary optimization can be built on top, proprietary backends can be built on top, so that it's really like an ecosystem that is growing up, building similar to what we see in the cloud space, a really good solution to bring AI models to edge AI systems. And so we decided to go for MLIR and IREE because we really believe in this technology, and this is just like one kind of idea on why we did this. Basically going back to the two dimensions that I just talked about on hardware flexibility as well as framework flexibility or model coverage essentially. And we believe that comparing it to other open source technologies out there, MLIR and IREE provide a very good stack and future-proof stack in both these dimensions, and also allow it to be integrated well with existing tool chains as well as tool chains that you might, for instance, build proprietarily for your specific IP or your specific chip in this market. And this is why we do believe that this is the technology to build on in terms of a community's idea, because it really gives these key values that you need in this market. And basically, just for all of those who don't know this, I'm not sure, most of you I think do know, but just a little bit of an idea here. What is IREE and MLIR? Actually, it's basically this idea of what LLVM and Clang are in the compiler space for conventional non-AI applications, that you have MLIR as an infrastructure layer that allows you now to integrate these different models and IP from an infrastructure perspective, and then IREE on top is building one specific compiler component so that you have the actual include. So I think this is reiterated for most of you, so I won't go into further details there. But specifically, how does IREE work? And this is also how our toolchain works, because we build on top of it. So you have the compiler component, and then from there you generate two pieces of artifacts. Number one is your host code. The host code is then running on a controller CPU inside your device, your HII device that all of you will have. It can be basically targeting ARM, x86 or RISC-V host CPU, so anything that you want is possible. And this host code then does the orchestration of the actual compute and is executed through a small C-based runtime. And then the second part is to actually generate the kernels for your specific workload that you're targeting. And by that, you basically have this runtime that is flexible to be extended towards different targets. I'm going to show this in a second. And in addition, you have the compiler toolchain to generate kernels for these specific targets. How does the runtime enable this extensibility? And the important part here is this hardware abstraction layer. So the hardware abstraction layer, or HAL in the IREE space, really enables the integration of different targets. So it provides an interface basically modeled after what Vulkan did in the shader space to really integrate all these different devices. And it's very easily to extend. So I think for most cases, if you take a look at your hardware, you should be able to just easily write an HAL kind of interface to that. And so this really enables you to integrate all these different devices from a flexibility perspective into your runtime, and then build a compiler component on top of that. And this is why we think that it's a really powerful kind of infrastructure to build this retargetable technology on top. So how do we integrate all this into one flow? Basically we start from the model that the customer brings. It can be trained, it should be trained obviously has to be trained, but it can be quantized. But we basically support any kind of quantization at that level, and it can be in PyTorch, Yext, TensorFlow, whatever you bring. And we have importers into our AI compiler technology. And then two things are happening. Number one is the optimization of the model execution. So here we're looking in step 2 and 3 into the workload optimization, as well as the execution optimization, more at a graph level, modeling the tensors that you need. So really these high-level optimizations that you want to do, and then place it on the specific host and target inside our system. And doing a scheduling between all those components. And then in the second step, so what is basically 4 and 5 here, is to generate then executable code for the specific target that then can be done through different pipelines that we are going to use. So if you, for instance, think about a CPU pipeline, I'm going to show that in a second, but essentially you want to generate code for your CPU. So you start, for instance, at the level of LVMIR and use Clang to basically generate your kernels at that point. And so what you get here is you get your host code, you get your target code, you combine those together, and then inside your inference engine, you can just run the code. And this overall tool chain built on these, technologies that we can all use, but also these really extendable interfaces now allows you to integrate new components from a hardware perspective, but also to integrate new AI models from a coverage perspective if you want, because it's relatively easy to extend both on the very high end of the graph optimization as well as at the very low bottom end of the specific hardware targets you're looking into. And just to give you one example of like how does a code chain then look like, I just brought the one for the CPU today. So basically it's a very off-the-shelf tool chain, so nothing like super unique about it. And I think that's a good thing because it allows you to extend it and allows you to work with it. What it basically boils down to is doing good memory planning and good tiling of your workload towards the actual cache hierarchy or the memory hierarchy inside your system or the compute that you have inside your system. So we start with this configuration phase where we get in the data about the target that we're looking into, then distribute our workload across a multi-core grid, tile the workload fitting to both the multi-core grid as well as the cache sizes that we have inside this hierarchy. And then, you either use vectorization to generate code or microkernel calls for parallelization. And then at the end, we bufferize this all to lower it through LLVM and link it. So basically, this just gives you one example of how to run this. The GPU pipeline looks a little bit different, but similar. At the end of the day, it's a really easy to extend system where you can see if you now have more cores inside your system, you can just compile for that, as well as if you have a little bit different hierarchy, all your heuristics still work. So that's quite nice in terms of the code generation pipeline. So now we have taken a lot of looks into the hardware side of things. So what does it mean from an AI user perspective? And from an AI user perspective, I think the most important part for them is if they buy a chip today, what they want is they want to go on Hugging Face and see, my model just runs. This cool model that I found there yesterday evening because I browsed LinkedIn or Reddit and everybody was talking about it, it should just run on the hardware. And so that's the key promise that we are trying to fulfill with our toolchain, that we really are able to provide a software development kit that is able to support these constant updates of models and is able to support all these small changes within these models that are always happening. So what we internally basically do is we monitor what happens on Hugging Face, use this as a regression suite against our compiler toolchain and check that everything always works within this monitoring of Hugging Face. And what this practically means is you can take a look at what's happening here. We always take Torch Inductor as the PyTorch compile solution as a baseline and think, so we have to meet what Torch Inductor offers, because that's what the customer would see if they would just use PyTorch and don't think about any specific deployment solution for the chip that they are running on. So basically everything that runs in Torch Inductor has to also run in our SDK, and for this like top 10 models that we at some day selected from Hugging Face, that's what we can support. So we could extend the list. We are way beyond top 10 at the current development time, but I think that's not the interesting story to support like a relatively static list of the top 10 models. The interesting part is when do we support a new model that comes out? And we just have selected 3 examples here, Llama 3.2, Small LM, as well as the Quencoder, and all of them were running within 1 day after being released on these platforms. So that's really nice to see that if we bring in a new model that is also maybe a hype model in social media, we can just check it and yeah, it runs within a day in our tool chain. So this is something we are really proud about and think is a core value that we bring here. Of course, this doesn't mean anything if the performance doesn't meet standards, and we do meet it. So what you can here again see is the comparison against Torch Inductor, both in terms of the memory footprint as well as the latency to run those models in an inference run on an AMD desktop grade CPU. And yeah, basically everything that's on the top right is improving both dimensions, and you can see that we have some okay until significant improvements in those 2 dimensions for those different networks that were also reported on the previous slide. So that's quite nice. And then for specifically looking into the edge AI space, so we are also having some comparison against TensorFlow Lite, where we have a lower overall improvement because TensorFlow obviously has this manually very well optimized kernels here, but still some improvement is possible. And then for like just the legacy kind of models that we might want to support, like a ResNet or a mobile vision transformer, we also see some improvements compared to Torch Inductor here for a mobile ARM platform like Raspberry Pi or Pixel 8 Pro in terms of the compile solution. So yeah, so this is something where we see we have this flexibility to support all these models, but we are also meeting the performance targets that we want. Another quick showcase on what our toolchain is able to enables in general to achieve is we took the Raspberry Pi 5 GPU, which is a Broadcom GPU and has a SPIR-V interface, and thought, okay, can we support this for AI workloads for GPU? And yes, we were able to do this within a very short development time. So basically, we were able to unlock this GPU for AI workloads. This is really more a showcase of telling you how fast you can integrate new hardware rather than go do your AI on the GPU. It is done for graphics. It's not an AI GPU, but it's possible to run general purpose workloads. And so basically we integrate, so the SPIR-V interfaces are nicely integrated within the IREE toolchain. And what we then did was additional optimizations. So this is like around 1 or 2 weeks of one engineer working on performance optimizations as a showcase how fast you can improve versus just integrating it. And yeah, so you see the gray baseline for individual operations is just off-the-shelf performance from open source, and then within a few engineering effort we could improve by 1 order of magnitude approximately. And this also relates towards running full networks on this GPU. So here again you have a similar performance improvement, sometimes extremely high, sometimes not that high. So this is a really nice showcase in terms of how fast you can support new hardware. And as a final thing for today, I brought you some insight also on what we're doing in the LLM space for edge execution on LLM. So this is preliminary data that I'm going to show from like what we did last week, essentially the development snapshot. But what we are doing is we are looking into Llama CPP versus an MLIR or IREE-based compiled solution for quantized LLMs running on edge systems. So for Llama CPP, just giving you some overview how it works. I don't know whether every one of you knows this framework. Essentially, it's an open source framework similar to TensorFlow Lite for LLMs. So what you do is you take your model, you export the weights of your LLM, you apply your quantization, and then you store it in this GGUF data format. And then afterwards, you can use Llama CPP as a library to execute this model, basically targeting specific kernel library calls. And this supports some specific quantization types, just listed 2 of them here. And the advantages is it's really fast, handwritten kernels, obviously, and it has support for various targets and optimization techniques. So you can take a look at the project. It's quite famous. Disadvantage is that it's actually really lengthy in terms of the development of new models. So for instance, OpenARM took months to be supported. There's the GitHub link to the discussion, how long it took the developers to support it. So it was annoying for everyone. And one part is basically also it's an explosion of complexity, right? So if you have layers, you have quantization techniques, and you have targets. And this just, you have to basically handwritten kernels for all of these. And so this is what we are trying to solve with our compiler. And so what we have achieved for now is we can basically do the same thing that Llama CPP can do. So for us, it's basically you download and export your model from Hugging Face. We match the quantized layer, insert in the quantization, in the compile framework, quant and dequant nodes, and then compile. And then we just run it with our toolchain, as I showed previously. And advantage from us, we basically support various types of quantization. So you can select the block size, the bit width, the asymmetric, symmetric quantization. So what are the advantages of this? It's much more flexible what Llama CPP provides. And also in terms of quantization, but also in terms of maintenance, because now you don't need to have all these specific matches of like target plus quantization plus your layers, but basically if you want to add a new quantization, it's parameterized into our compile toolchain. Obviously, performance is an issue if we do such a generic approach. Be very transparent about that. We are not there yet. Today it's slower than handwritten kernels for certain models, but it's improving currently. So this is the snapshot of Friday afternoon. I took the latest data that we had. So basically what you see here is in white the throughput for Llama CPP, in red our throughput. You see two things. One is baseline execution with full floating point arithmetic, and then we have also the optimized execution with integer arithmetic, so quantized to specific, so where everything's quantized. So yeah, you see the throughput is still lower. That's for granted, but that's work in progress. But we are getting there, and I think that's a really neat process to see. So for decode, it's not far off, as you can see at this point in time. The difference isn't too large. And then also for the prefill phase with the optimized execution in integer arithmetic, we are also really close. And just to give you an idea, we haven't invested a lot of time into this. This is like 3 weeks of one engineer of us working on this full time. And we are already close to the performance of handwritten kernels of Llama CPP, which is a 1.5-year-old project. So this really shows how performance or capable this the platform that we are offering actually is in this regard. So this is just an insight on what we are doing on a day-to-day basis. These numbers will get better, and then we will also officially publish them. Okay, so to wrap this talk up, how do we integrate all of these? Basically, we want to provide an easy-to-use solution for ML developers. So again, thinking about the ML developer or the embedded engineer who just wants to execute their model on the platform. And so what we are working on is having the software development kit that includes the compiler, the runtime, these different support for quantization techniques, debugging, tracing, as well as the benchmarking suites, and then everything integrated into a Python API. And then you can run it on different targets as presented. And yeah, with a lot of customer interaction that we are doing in this per month, we are getting the insights that we need to build this, and it's a constant process of improving there. So thank you for your attention, and I'm just open for questions at this point.
Do you have some high-level profiler or is it in the pipeline?
Sorry, I need to use the microphone. We are using the normal profiling tool. So for instance, for this BAV example, we just used the profiler that was given, that is open source available for the Broadcom GPU, that was sufficient. And for everything else, we just use the normal profiling tool. So it's integrated within the pipeline, so you can check it from the pipeline, but it's not like our own profiler, if that was your question.
Maybe time for one question. The question from YouTube again.
Yeah, cool.
By Javier, how is the hardware information added into the compiler toolchain in order to take it into account for the model cost offloading, even to the internal accelerator, or how to decide to use the hardware?
Yeah. Okay. So that's basically two questions. Number one is on how to integrate the parameters of the hardware. So basically that's something where we do have profile files that you read into our compiler. So it's not something that the user can set at the moment. But yeah, easily to extend. Regarding selecting the hardware, I think that's at the end not only given by the compiler. People do select the hardware not by recommendation of the compiler, but usually by selecting a specific target. For us, if you run our toolchain, you can just select the target and then it generates code for this, but it doesn't help you with the selection automatically.
Hey, thanks again for it.
Cool.
Interesting talk.
Optimizing performance, yes.
So let's move to the last speaker of this session. We have Alejandro Carmona Martínez. He has conducted over the last year the research towards automatic generation of optimized code by using MLIR to further improve the performance and usability of tensor cores and other accelerators. He holds a bachelor degree in computer science from the University of Murcia, where he's currently also working towards a master's degree. Along his studies, he also serves as a graduate researcher at the same institution, and he's giving us the feedback that he believes CODAI 2025 is a great and fantastic platform to exchange insights on leveraging domain-specific accelerator and MLIR. Thanks for the feedback. And go ahead.
Well, okay. So first, thanks to Miguel for the introduction. I want to also thank both my advisors, José Manuel García Carrasco and Gregorio Bernabé, for their help with this work. And now let's start. Okay, so first, let's zoom out a little bit. And I want to talk about a really unknown issue, Moore's law. I know it's a soccer, but it really is the bottom of our problems. What I mean is that industry realized that CPU was not scaling anymore, and they decided it was time to move on to domain-specific accelerators, specifically for these fields like deep learning, where computing is really demanding. But the problem now is not with the power of the hardware itself. It is in how we can extract the most from it. In this slide, we can see that I believe CUDA and NVIDIA really hit their stride with CUDA because they allowed for a computing model to extract all the performance from their accelerator throughout their throughput. And CUDA cores are really great for these parallel workloads. However, NVIDIA really realized that, yeah, thank you. I didn't even realize.
Now we know how to do it. No.
Okay, thank you.
Sorry about that.
Yeah, I think I am also moving away a bit from the mic, so maybe it's good I stay here. Okay, so what I was saying, CUDA cores work really great with these parallel workloads, but NVIDIA really thought that it was time to move on into a specific circuit in order to better target the workloads of deep learning that are mainly based on matrix multiplication and accumulation. And that is how tensor cores come to be, and they are really great at doing that, hitting up to 8x of performance over the already good performance of the CUDA cores. See, I think.
Click on the slide once because focus.
Oh, thanks. Okay, so tensor cores. Tensor cores also get their power and their throughput through their shorter data types. They utilize shorter data types such as FP16 and FP8 in order to increase the throughput. However, they are not working natively with FP32. If we were to work with FP32, we'd have to utilize CUDA cores if we want full precision. However, as we will see later, there are a few workarounds with that. Also, I have a bit of a grievance with how tensor cores were utilized. I mean, I believe that in order to extract the most from an accelerator, we have to hit the 3 Ps: portability, precision, and performance. And as you see by the red crosses there, I have a bit of a problem with each of the current ways to target them. Well, first and foremost, the most common way to target tensor cores is through the vendor libraries. They are quite nice, actually. They hit the most performance, and they are really easy to utilize, whether on C++, Python, etc. But they also tie their code to whatever the implementation of NVIDIA is. And if I wanted to port my code to perform in matrix multiplication on any other environment, I'd be a bit tied up. So if I want portability, okay, I can move towards an AI development tool, such as PyTorch, TensorFlow. However, then I'd be a bit restricted because sometimes on these tools we cannot have all of the performance because some of the fixed instruction sets are already there. So if, for example, I want to utilize FP16 on PyTorch, I may have a problem, as we will see later. Well, finally, you could also utilize the dual VMMA API. However, this is not really a very productive way to produce code. So I'm going to, to move on now. Okay, now a bit of change of pace. Normally here in this part I introduce MLIR, but now I'm preaching to the choir. I mean, I think all of the assistants here already nominate MLIR, so let's highlight what I am interested in telling. MLIR dialects really allow for us, the compiler programmers, to go from very high-level specifications to really lower-level ones. And that is a really key functionality that I think we can exploit to further exploit tensor cores and maybe other accelerators too. Currently, I don't believe there is another dialect that allows tensor core multiplication out of the box within MLIR. So we have to go through a down conversion, through a lowering process. And in that manner, I believe that there is an easier way to go. In our research group, we, for the few previous years, we've developed, well, it was previous to my arrival, but my research group developed HDNN, which is an MLIR dialect that allows agnostic computation. And it is really, it is the dialect that we've chosen in order to, as you may have already know from the title, implement the CuBLAS tensor cores into MLIR. We could have chosen any other dialect, and we have to perform the lowerings in that dialect, but we were already familiar with this one. So that is basically the gist of our proposal. We want to use tensor cores within MLIR. Specifically, we want to utilize tensor cores through the CuBLAS library because we believe it gives out the best performance with the easier way to program. And we want to highlight a few of the hurdles that we have to go over. I commented already that tensor cores base their performance on the data types that they use. And in this case, we have focused on FP16 and FP32 precision. So what we've done is to allow the user to have a few different modes. So it can utilize FP16 precision, FP32 precision, but in order to utilize FP32, we'd have to down convert these inputs into any of the compatible formats. We could also have other data types, but those are the ones that we chose to focus on. And finally, in order to allow for a full precision FP32, we are also going to offer support for the CUDA cores. So let's get to the meat of it. Here it is like a high-level representation of what we are trying to achieve. We have, on one hand, MLIR and the other tensor cores, and we've chosen to go with our MLIR dialect to exploit MLIR, and with the CuBLAS C++ library in order to target tensor cores with that library. So what we've realized is that we needed to bridge those two worlds, and in order to do so, we have to build each part of the bridge on each side and then connect them. So on first, we have the MLIR dialect that, as I tell you, we chose HDNN, and we'd have to implement a front end for the operation. And this operation will also have to deal with the MLIR data type ecosystem and then perform a conversion to what we are going to use on CuBLAS, but more on that later. The important thing is that we are having to define both the front end and the lowerings in order to have a lowering to LLVM IR that in turn is actually calling to CuBLAS in the end. So that is what we're going to do, also helped by other dialects such as the GPU dialect. On the other side, we're going to develop a few of the CuBLAS operations, and we are going to make these two parts talk through our wrapper that will allow from the lowering to LLVM IR to call to these operations on CuBLAS. Okay, so this is also a high-level representation of our front end for the operation. This is the operation that we are going to utilize. It is a regular front end with support for all the types that we are going to be utilizing, in our case, FP32 and FP16. We'd also like to highlight that this is a device agnostic implementation. This operation could actually be lowered to any domain specific accelerator of our choice, but more on that later. Sorry. Okay. So what we've done is having a CuBLAS, C++ CuBLAS implementation that allows us to perform these calls. So we have these C++ functions that will receive a few arguments, and this will be thrown from our MLIR pipe stack. And in doing so, we'll be able to pass all the arguments that we like. In this case, we are talking about FP16 data, and we'll be using FP16 data, so it is quite straightforward. However, if we were to utilize FP32, we'd have to do a down conversion that in our case, we are going to do in CuBLAS, within CuBLAS. So for MLIR, it is going to be an opaque process, and actually, it will not even notice that the FP32 data has changed. The conversion will just be done within the CuBLAS part of the pipeline. Okay, so in this part, I try to detail a bit of what the MLIR wrapper, CuBLAS wrapper is doing. As you can see here, it does map the conversion of the MLIR functions into, of the CuBLAS functions into MLIR and vice versa. It starts with registering these CuBLAS operations as MLIR calls, so we can perform the calls from the MLIR stack. And also we'll be able to perform the conversion from the LLVM IR data types to the C++ CuBLAS data types. So in summary, what it's doing is bridging a bit of the two gaps. Okay, in this part, I try to also offer a pseudocode of what is happening in the lowering. What we are doing here is we are utilizing the GPU dialect in order to initialize the GPU stream and also the tensor structures. And then we are going to utilize our developed wrapper in order to perform the calls. Given that we know the data type, we will find out about the shapes of the tensors and call the pertaining operation. Okay. And when it's all said and done, we end up with something like this. This is the LLVMI IR code that is actually performing the call to the C++ function. In this part, as you can see, we have all the previously developed instructions here, driven down to the IR, and then finally the call to CuBLAS through our wrapper. And I also like to highlight that I've not talked about CUDA cores, but what I wanted to introduce is that it is quite easy to just take our whole pipeline and perform a little modification on the CuBLAS part of the stack and just have it to also target Tensor CUDA cores, so we can have FP32 precision out of the box. Okay, so here is the testbed of what we've utilized. I want to highlight that we've used the NVIDIA RTX 4090 because it has support for the TF32 precision. And sorry, I'm getting back to the mood. And I also want to highlight that we are going to compare against PyTorch as of now. I think I skipped a slide, but I'll come back to that later, and I'm going to interrupt the flow now. So let's start with the results. Okay, so here in this plot, we have the different performance of all the tensor cores and CUDA cores combination with different data types. The green bar is for the FP16 tensor cores. The blue one represents the FP16 with down conversion to FP32. And then finally we have on the red one, the TF32, and yellow for the CUDA cores. So as you can see, the highest performance always belongs to the FP16 tensor cores because they are able to exploit more of the more of the throughput. But we can also utilize FP32 close to the announced peak performance on the datasheet for tensor cores with this accumulation of TF32 and FP16. And finally, I'd also like to highlight that while CUDA cores have a similar peak of performance as the conversion to TF32 for tensor cores, they get a bit of a performance difference because CUDA cores cannot actually perform as well the matrix multiplication, at least on the kernels. Okay, now to our plot comparing the performance that we are getting with our proposal. So in this plot, we are comparing against CuBLAS. It is normalized to the speed up that we are getting with CuBLAS throughout all of the configurations and data types. And as you can see, there is no performance difference in any of the configurations. So we can say that we are not inducing any overhead throughout all of the different configurations. Then we can compare against PyTorch, and there are some interesting points to discuss here. As you can see, for the lower dimensions, PyTorch actually performs considerably worse, at least in this plot. And we can see that this overhead is disappearing throughout the increasing dimensions. That actually means that PyTorch is inducing some overhead for this lower dimension, but it is to be expected as PyTorch does not care a lot about performance on these kind of computations. For the other important point is that when talking about FP16 performance, PyTorch does not allow an FP16 accumulation even if we are utilizing FP16 data. However, we can easily allow that utilizing MLIR and CuBLAS, as we've seen, so we can actually exploit more of the performance of tensor cores. As you can see, we can get up to a 2x speed up. And there you could say, okay, so what about TorchCompile? Because TorchCompile can actually improve the performance of PyTorch. Well, TorchCompile is really more of graph-based. So what it's actually doing is taking the eager mode and turning it into a graph mode. And while it can improve performance on specific kernels utilizing Triton, in this case, it actually does not perform better and ends up defaulting to the CuBLAS implementation, which ends up being the same as the implementation that we are using, but from the FP16 case that I've commented already. So that gives us a bit of the overview of the performance that we've achieved. Okay, so on to the conclusions now. Here I try to expose a bit of what we've done in a slide. And I talked earlier about the 3 Ps of performance, portability, and productivity. Well, we believe that by putting an MLIR layer over the CuBLAS vendor library, we can actually achieve the 3 of them. We can combine this great performance that we can get with specialized kernels with the portability that MLIR allows us to port different codes to different accelerators. The performance, as we've commented already, has matched that one of CuBLAS throughout all of the different implementations. Moreover, within PyTorch, when they cannot utilize FP16 accumulation, that is in fact due to a convergence issue when they really don't like convergence issues in training, so they don't allow for that. It's also a design choice, but it shows that we are limited when we are talking about portability in that field and performance, sorry. So even though we utilize TorchCompile's results don't improve that much, and even they lose a bit of performance when the dimensions are smaller due to the induced overhead of capturing the graph. So the future work would actually take on utilizing the previous work that was developed to build backend compilers on top of the stack that we already have, or domain-specific languages that allows us to utilize domain-specific accelerators, utilizing their vendor libraries so that we can abstract that part from the compiler designer. So thank you very much. These are some of the references for the external picks that I've used. And now I'm ready to field the questions, so please feel free to ask anything.
think you have time for one question. Yeah, questions in the audience?
Sorry, can you repeat?
Sorry. It's possible to compare performance with PL, for instance, or
Yeah, well, you are referring if we could improve performance by combining TVM with our proposal. Well, that's a very good question. I tried actually with Torch Compile, I had a bit of the hope that it could write an improved kernel, but when I realized that in the end it was calling to CuBLAS, I think that for these very specific kernels, actually it is difficult to beat the performance that NVIDIA is offering because they know the product throughout and they can actually do some of the more specific improvements. However, for other domain-specific accelerators, I think TVM is a fantastic choice to have a good performance for all of the operations. So have I answered your question? Or... So thank you for the question.
We have time for one more question. There. No more questions, then. Thank you again. Thanks very much. I think now we have a coffee break on the agenda up to 4 o'clock, so it gives you around 30 to 35 minutes to grab some of these. See you back in countdown.
There's 3 minutes past. Okay, welcome to the last session for today. We have 4 more presentations. This morning it was way too cold. Now we have temperatures like Barcelona in summer. It was worth complaining. So okay, our first talk is given by Chen Liu. Chen Liu received his Master of Science degree in Microelectronics from the University of Dresden in Germany in 2016. He is currently scientific staff and is working towards his PhD degree, the chair of highly parallel VLSI systems. His research interests include intelligent radar, signal processing, efficient deep learning, and AI compiling. And he's going to give us an amazing talk about a lightweight C code generator for heterogeneous tiny ML systems. Please go ahead.
Thank you. Thank you for the introduction. And also I want to thank for the funding part. This work is funded by the BMBF with the project of the events and also from the DFG. So I'm glad to share my work for this lightweight C code generator for the heterogeneous tiny ML systems. So here is the outline. So I will first begin from where this story starts and then show some state of the art with the current solutions. But unfortunately, at that moment, when I searched that none of them really fulfill my requirements. So then we go to the methods, how I design my code generator. And I bring one case study, which is the DNN model for the experiment. And we compare in the results for the different metrics, and then we conclude the work. Okay, so the motivation. So in the year of 2025, we all know that we have mature training frameworks like TensorFlow or the PyTorch, and people use GPU to train the model. And but usually in the real world, for the application perspective, we tend to do the inference at the edge. And in this production environment, the environment there is quite different with the training environment because we have usually limited resources. Let's see, limited memory, limited compute, and limited power budget. right? And in our chair, we are IC design chair. So usually we design some edge devices or edge chips for different applications. And we see some unique requirements by doing this deployment phase. So even though that we have a well-trained model available, but still it requires a lot of effort that you need to shape your model and then deploy that on your target device. And especially we observe some requirements in our case study here. For example, if our hardware team designs their chip, and usually the toolchain is determined in the development phase. So in our case, for this case chip, that we expect pure C runtime, so without any C++ dependency. And second one is that this chip is actually for some radar applications. So this is a real-time application. And for real-time applications, usually we expect very high efficiency for the inference because we only have limited time for each frame or each time window. And the third one is that after we have the chip and we deploy once and we want to test maybe varied models, and the model can change a little bit, but we want to reuse our deployment phase with this floor. So we also target the reusability. And the last one is that we want to minimize our manual intervention. So basically, we want to set it up and then forget it. So one click, we want to bring that in a loop for the multiple deployments. So with these four unique requirements, we check out some state-of-art. I categorize these different solutions in 4 clusters. So the first one is some enhanced toolkit from some mature frameworks. Let's see Glue or XQTorch from PyTorch community, TensorFlow Lite Micro from TensorFlow. And the second category is some toolkits provided by the chip vendors. Let's see EIQ toolkit from the NFT, STM32 CuBLAS from ST Microelectronics, OpenVINO from Intel. And third category is from some compiler frameworks and also the MLIR-based frameworks. This is actually have a rising tendency only in the recent 1 or 2 years. And we have tried the TVM4 and also the IREE4. The fourth part is some third-party solutions. I know that there's DeepC and library Onyx for that. But as I said, that if we have a customer edge device, let's see, especially in the academia, it happens. People usually design some maybe it's a tiny device, right? It should be small, but it should be novel. The novel means that you have purely new hardware block. And the new hardware block also needs a new API from the software perspective. And if we have these 2 requirements, we usually tend to require some PRC runtime for easy debugging. And also, we expect a high efficiency. The high efficiency comes from 2 perspectives. One, it can be from some accelerator, which by self-design for some optimized for specific applications. And second thing is from some IR optimization techniques. And we also try to achieve this reusability and automated pipeline for that. But if we look at both sides, and if we want to merge them together, we see some challenges and mismatch between them. Because if we look at these solutions, some of them, they only have C++ kernels, so you have C++ dependency. And these commercial tools, they only optimize for their own products, and it's not really friendly to the public community. And also, some frameworks, they target some general purpose backends, and rarely touch this accelerator, especially some domain-specific accelerators. And we also observe some, if you need a new dialect in MLIR ecosystem, it also requires a lot of effort. And we also observe there's still some optimization room based on the current solutions. And I will introduce 2 unique optimization techniques that we apply in our tools. So that's why we tend to propose this lightweight SQL generator for the heterogeneous tiny ML systems. Tiny ML means that our chip maybe is only bare metal because we are from the academia and we don't have such powerful support for the operating system. And heterogeneous means that this chip can often mount it with an accelerator for specific purpose. Okay, and here I try to give you some introduction about this code generator. It is Python-based, and we divide that in 4 modules. So the first one is the front end. The yellow box, this is some required inputs from the users. So you need to prepare a trained model. Currently, we interface with the TensorFlow Lite, but we also observe that in the current state, PyTorch is more and more popular. So maybe this Onyx support is also in development. And you need to prepare some input samples for the trio inference. In the backend, you need to prepare a template site, which is some template C functions that's supported by your accelerator there. So from front end, you need these files. From the back end, you need a template for that. This is the 4 main modules of that, and 3 user imports requirements. And finally, it will generate the C runtime, which is in the main.c file, and also according to your output config, you can export these parameters or IRs to different formats. It can be writing into some arrays in C headers, and also can be in JSON, and also can be in some memory, binary memory formats. So here, I will first introduce this front end. So the front end is basically a parser. I will use this TensorFlow Lite interpreter to parse this model, input model, and it will parse layer by layer, and you extract those key tensors to store that into a dictionary, and we extract those inputs, weights, bias, and outputs, and we'll store that. And if this model is a quantized model, because in H applications, usually quantization is a default technique that you will apply. So we will also introduce, we also extract these scaling factors and also the 0 point for the quantized models. And besides that, for different layer types, you may also have some meta information. For example, for convolution layers, you have some like stride or kernel size for that, which will also be allocated in the attributes. And then after you have this extracted intermediate representations there, and next step will be to do the IR optimizations. Here, the optimizations is not the common mentioned optimizations like already applied in other frameworks. Let's see TensorFlow Lite or TensorRT already try to squeeze some specific patterns. Let's see convolution plus batch normalization plus ReLU, they will fuse that into a single operator. So it doesn't mean this is not what I mentioned here. I mentioned here, I suppose that this already performed by the other frameworks. And if this is already quantized that, we observe that, for example, you have two continuous quantized nodes. And you see that usually, even you quantize each layer, and you still need insert some dequantize and quantize operators there in between for the risk scaling purpose. And this risk scaling purpose, this can be consists of several scaling factors, and this will be in floating point. And that means you need a floating point unit to perform this risk scaling. And we propose this weight tuning technique to save this parts. So how we do this? So suppose we need to do this risk scaling with the product of SXXW, which is scaling factor of input and weights, and divided by the output scaling factor. And this scaling factor can be always defactorized with 2 values. One is what we call it S-tune, and S-tune will be always in between 0.5 to 1, and with a redshift or left shift, usually it's redshift, shift operation after that. And this S2 value can be merged into your quantized weights here, and this can be we can get this new merge, so tuned weights there, so that we can transform this calculation with risk scaling to pure integer-based weighted sum, which can be supported by the accelerator. and also with redshifting. And in some specific accelerator, at least in our accelerator, we already support internal redshifting operation at the output of the weighted sum operation. So basically, this whole part can be supported by the accelerator. And let me give you some example. Is that suppose you have these values as this scaling factor, and this scaling factor can be always equals to 0.56 with a 6-bit of redshift, and this 0.56 will be multiplied to 130, so you get this new scaled, so with tune width, and with a 6-bit redshift. So that's the first technique we applied for the weight tuning. The second one is called bias fusion, because as I said, that's this weighted sum will be calculated in the accelerator, and if the redshift is also supported by accelerator, and in between there will be a addition sum. And how can we save that part? Because the bias, it is also static values. So we can bring that also in the ahead of time optimizations. So this is bias vectors can be defactorized to additional column and rows in the input and outputs. So in this way, we just need to expand additional dimensions for the input and width, and then we can perform that purely as a weighted sum operation. And this is example in the fully connect layer, and in the convolutional layer, we just need to pad with additional channels there for the bias. So with this transformation, we will get only a pure weighted sum operation with a shift operation. So we can perform this both weight tuning and bias fusion for this IR optimizations. And this really brings some compute efficiency there. I will show that in the results. And then we continue for the third module, and this module we call it DSA optimization. So there's some optimization required for specific hardware. So it's really hardware related. If you change your hardware as a backend, you should also change this part. And for our accelerator, we perform this check. So the first one is an assertion of the layer configurations, because your hardware only supports limited resources for the input, the tensor. So we will check whether the input tensor size or the kernel size, whether they match with the support of the accelerator. If it's not, it will raise error. And the second thing is that we see the TF Lite will give you the channel last as a default data format. But our accelerator supports the channel first. So we will also reorder this channel formats here in this stage. And this will be performed ahead of time. And third one is weight layout adaptations, because our accelerator supports some specific memory layout for the kernel weights. And if it doesn't match the default TF Lite stored weights, and you have to reorder that, this will be performed in DSA optimization. The last one is for the memory alignment, because the accelerator usually fetch multiple data at one fetch, and you have to make sure that the data aligned correctly for the computation. So we will pad to this the data to the 128 bits aligned for the fetching. And after this DSA optimization, the last part is this code generator. The technique we use is a template-based code generator. So we use the Jinja, which is a library for the templating. So with this Jinja library, you can easily template your C functions, which is the API functions provided by the accelerator. And it's a mixture of the static part and the dynamic part. The static part is some configuration tests that you should do for each execution, right? But the assignments for the real values of each layer, this is a dynamic part, will be parsed by this front end and then reshaped by the IR optimizations. And here assign it to the real configuration registers. So this is templates that you should prepare, and this is generated code for example of fully connected layer. And for each layer type, you need to prepare such a Jinja template. So you will prepare maybe for your model, if you have such kind of layer types, you need to prepare these templates and also the main function for that. And basically that's all what you need for this code generator. And then if we have this tool, I introduce a case study as an experiment. So our case study is for radar target recognition. So this is the requirement from the project. And this classification will be 4-class classification: vehicle, pedestrian, cyclist, and noise. And we just developed a very tiny CN model. We call it the RadarNet, and it has only 9,700 parameters, and it can be successfully quantized with integer 8 for static quantization, and it achieves 92% as accuracy, so acceptable for the applications. Here, this figure is the model structure of that. We see that basically it just contains the COM2D, max pooling, and fully connected layers. And besides that, we also introduce this static memory planning. So in this case study, it's quite simple model. So we have just a sequential floor of the tensors. So our static memory planning is just a ping-pong buffer strategy. We set up 2 buffers, buffer A and buffer B, and you will see the data flows from the first input tensor from activation 0 and 1, 2, 3, 4, 5, 6, 7, 8, 7. And we just divided it in 2 groups, in 2 rows, and check where is the bottleneck of each rows and pick this size as a buffer size so that we can reduce the same buffer size for each intermediate representations here. So that's the ping-pong buffer strategy for the memory planning. And then this is the backend chip that we use. We developed that. This is from my hardware colleague developed for this radar DSP. It contains 6 12-bit ATCs to convert this analog signals to digital. And it has the GTAP UR SPI as the data I/O. In the processing topology, we see it has in total 25 processing elements. And in each element, it has a basic RISC-V core, which is an open source core, and 128 kilobytes as a SRAM. Most importantly is that we have self-designed accelerator, which is a machine learning accelerator. This is a 4x16 microarray, which can support the gene and convolution with either 8-bit or 6-bit integer calculations. So that's the resource that we have. And we tend to just deploy this RadarNet, this small model, into each PE so that we have multiple detections in the same frame, in the same radar frames, and we use each core to classify whether it's some noise or some other interesting objects. And if you are interested in this hardware, and you can refer to this paper for some details. And here is the results. So we will benchmark some metrics, including some execution time. This is clock wall time, and also the binary size, which is compiled binary size, and some manual intervention. The manual intervention means that how much effort that the user should put on this code generator to generate the desired code. So we measure that with code lines. So first one, we compare this to candidates. This one is a micro TVM. So micro TVM is a subset of the TVM floor, which is especially used for the bare metal embedded systems. And they only use this CPU as a backend. And our code generator will use the CPU and also this machine learning accelerator for the convolutional layer and also the dense layers. And you see that for the execution time, we actually achieve a good speed up. One of the reasons is because we additionally use this machine learning accelerator, makes sense. And second factor is that we perform this IR optimizations, right? So it achieves a lot. And for the binary size, we also have around 40% reduction of the binary size, which is good for the small edge devices because the memory there is quite valuable. And if you have a smaller binary size, always good thing. And for the micro TVM, you don't need much manual intervention because it's already available compiling tool. But in our code generator, for those max pooling or convolutional dense layer, you need some pattern for there. So you need some manual intervention there. I will introduce some details here later in the next slide. And then we go one step further. We compare these two things. The one is micro TVM plus UMA. So UMA is a universal machine learning accelerator interface which can elevate the user effort to easily register your own accelerator into this micro TVM flow. And this is not exactly as the one that the student presented in our last year's CuBLAS workshop, but I further extended to support both fully connected layer and also the convolutional layers. And we see the time there. So even now we are already stand on the same page because we use the same accelerator, right? They use the same hardware resources, but still we achieve over 2 times speed up. And here, what's the reason here is first one, we additionally apply these 2 IR optimization techniques that I introduced. The second thing is that we observe that in the default UMA stuff flow, they convert this channel first to channel last conversion online, but we perform that ahead of time. So this can save some time. And this both factors bring some speed up here. And for the binary size, we further reduce 20% compared to this UMA floor. But the interesting thing is that for the manual intervention, if we compare how many code lines you need to implement for these tools, you see that we have to implement more code compared to the micro TVM plus UMA. The reason is that for UMA, you only need to focus on those operators supported by the accelerator. But in our code gen, you need to implement all operators contained by the model because we don't depend on any other external libraries. But UMA can use this TVM floor for those CPU-based operators. So you definitely need to implement more. But the good thing is that if you don't have further other new operators, and you almost doesn't cost any more things for you to further implement that. Okay, so that's the results. And I also want to bring some discussion points, which actually some concerns also from the review. The first one is about the flexibility. So I get some concern from reviews that people say, okay, you only show one model. Does it really limit your code generator? But I would say actually this is easy to expand to other CNN models without additional effort in case that this new CNN models contain the same layer types of that. So you can change any meta parameters of the CNN models like kernel size or the channel number of channels, something like that. And then in our code generator, you don't need to modify anything, just re-click and you get the new generated code. Only when you have new operators, let's say you change your model from CNN to another RNN model, and then you have to really re-implement some front-end processor. This is some effort that you need to put for changing to other input models. If you want to use the same code generator for a new backend device, let's say you share or you develop a new hardware, and what do you need to change? You need to change basically this backend specification because you have new hardware. It can support maybe larger feature map size, for example, and you need to change the specifications here, and you have to prepare a new template site for your new accelerator, which contains these C applications, APIs for your new accelerator. So besides that, I also think that in our case study, because it's a quite small model, and we don't really observe any accuracy drop after this IR optimizations, but we admit that this IR optimization will bring some truncation errors, and it can happen that for some complex model, you will observe some accuracy degeneration, right? And then we think that with some quantization-aware training technique, it can alleviate the drops here. And further one is that we want to declare here is that these 2 IR optimizations, this is not exclusive only in this tool. So it can be also applicable for other MLIR-based or TVM plus UMA-based flow. So if you have the human resources, you can implement the same optimizations for these MLIR flows and also UMA flows. That's possible. And then the last question is about people may ask, so when do I need this code generator, but not instead of the MLIR floor or TVM floor? I would say that if you have really some self-designed chip and you want to have a lightweight and no external dependency tricky solutions for that. And I think maybe this work is more suitable compared to the other compiler framework for your choice. So here is the conclusion. I developed a lightweight SQL generator, which is for the DN model deployment for the heterogeneous edge devices. And this is Python-based and easy to expand. It can generate the pure C code, and we use some IR optimizations to achieve the higher efficiency of the goal. And this work is all open source. You can access that in GitLab. And I want to re-emphasize that the goal of the IR optimizations is that we enable a full integer-based DNN inference on the backend. So it means that you can completely save your floating point accelerator for your backend when using this rescaling optimization technique. And this technique can also maximize the utilization of the machine learning accelerator. And with that, if we compare to another accelerator-free workflow, we achieve over 2 times speed up and 20% executable saving compared to this TVM plus UMA flow. So that's, we provide this lightweight tricky solution for DN deployment. And of course, we also observe some limitations of our current work, right? So first one is that currently this example model is quite simple. And if we want to bring some more complex models with some more complex graph, let's see some MobileNet or ResNet with residual paths. And this may involve new research. And the second thing is that our chip is actually a multi-core processor, multi-processor SoC. So we also want to spend more efforts to research on how to partition the IR to tile IR for the parallel processing with multiple cores. And that's basically all my work. Thanks for your attention.
Okay, so thank you very much for a great talk. We have virtually no time for questions. Maybe there is a short one. Otherwise, another short one.
Yep.
Who can do faster?
So I'm a little surprised that in an embedded environment you get performance improvement from bias fusion. Can you say maybe something about your accelerator, about what bias fusion is valuable in this?
You mean only the bias fusion or together with this weight tuning?
Yes, I heard.
Yes. You mean the question is that how I came up with the idea, or
no? Well, when you do the bias fusion, you're actually increasing the number of weights that.
Yes,
so
I increase
the number of multiplies that you
yes.
do, and you're increasing the number of data that you can remember.
Yes, but you only increase that with a little additional data. Let's see, if you have a huge matrix and you only add an additional one vector, let's see, and compared to the original one, it's a very tiny additional overhead, and we don't observe the relative high overhead on this approach. And only concern there is that maybe the truncation errors will damage your work, and you may be disappointed after you try this IR optimizations. And in this case, well, we think that with QAT that it can help you.
Okay. Okay. Thanks again very much.
Thank you.
What is this meeting?
Okay, so setting up, I already started with the introduction. So next talk is given by Shubham Rai, who is working with Bosch Research in Berlin, Germany. He works in the field of hardware software co-design for AI accelerators. Graduated with a PhD from TU Dresden, and got many prizes among DATE, DAC, TVOC, TDAC, ASAP, so very nice. And his talk is going to be on the topic of SRAM. In particular, the title is "What happens if SRAM should stay SRAM?"
Thanks a lot, Michelle. Thanks a lot, everyone. So, so this work is primarily we're doing the work within Bosch, and we found out that this this particular instance where we wanted performance, and in order to solve the memory bottleneck, we thought maybe this might be interesting to look into, and that's what we would like to share with you all, guys. Okay, so okay, so I think most of you are aware of this problem, performance and memory bottleneck. Like memory is one of the key issues in all the growing AI models. This figure is from 2022. It's a bit old, but I think it still is valid. And obviously the extrapolation would be further. So the parameters are increasing. That means your memory size is increasing, and also your compute is increasing. But the problem is the amount of data which you can transfer from your memory to the compute, that still is creating this bottleneck issue, which needs to be solved. And there has been other methods, like we have seen in the entire day, that bring this compute to the near to the memory and so on and so forth. But what if we have the compute within the memory itself, and that's by gaining for the in-memory computing. And from Bosch perspective, this has been one of the major requirements, that the number of TOPS is increasing with every level of automotive, let's say, I won't use the word supremacy, but let's say the amount of automotive intelligence which is going in. So from level 2 to level 2+, and so on and so forth, you can see the amount of TOPS which requirement is getting higher. And this memory bottleneck is not solving the problem. But with in-memory computing, the idea is that you can bring the computation within the memory to solve it and to see whether you can get the performance improvement. And normally the memory array is a matrix, but in this case, in-memory computing, you can have this vector matrix multiplication. In our in-memory compute macro, there were some assumptions which we took. So it had an 8-bit integer precision, and it is an SRAM which is configurable for 16 megabytes, 32 megabytes, 64 megabytes, and so on and so forth. In our use case, 16 megabyte was the most, let's say, most optimum in terms of performance per dollar scenario. Okay, let's get into the detail of the in-memory computing. So you can see that this is a memory array, which has like a grid of IMC macro and some external stuff. So this is the weight buffer, the input buffer, obviously the weight. So something will be stored in the memory so that you don't have to bring in those stuff again, and only the input is coming from the outside world. You have an LPDDR4 interface, which is the memory here. You have a shared L2 memory, where the feature maps are being stored. And in this direction, I think the animation is not working. So in this direction, there is the MAC-based operations which is happening, the COM2D, the dense operation, and so on and so forth. And this is where you have the post-MAC operations, such as the activation function, bias add, max pooling, and so on and so forth. So this is the in-memory computing architecture which we use in our work. Now, what I want to bring in, that yes, we had this interesting hardware, but just having the interesting hardware won't help it. So if you look back, we are almost covering like the first quarter of the 2000 of this new century, and then from the very beginning, we have not just relied on the transistor performance. We have tried to bring in the multiprocessors and so on and so forth, and now we are going to the AI world, where we have GPUs, NPUs, CPUs, and so on, and so many PUs actually. So here we brought in this in-memory computing, and we tried to see how we can improve it from the deployment perspective. And we brought in the hardware to software co-design approach. So here, the entire approach, what we looked into was having this entire space where we have the first step was hardware-aware NAS. We did the compression, and then we did the deployment. And then this was a closed loop approach. And in this talk, we'll primarily focus on deployment. We had an earlier paper which covered this entire flow. It was published in SOCC. And in this work, we'll just focus on deployment perspective. So from a deployment perspective, this IMC accelerator, we thought of doing these particular optimization. I think everybody knows here in this group. And this was basically the closed loop optimization flow, where we have the one-shot model from the NAS. and which gives us the network architectures. We do quantization and compression here. We do the deployment using TVM, and this generates frames per second of throughput of the latency here. And then again, this is fed back to the NAS. So this is the closed loop approach we applied to enable the hardware-software co-design. And here I will be focusing primarily on the deployment perspective. So what is the optimization target here? So from Andreas' talk, we have to maintain minimum to minimum data transfer for the in-memory computing. So IMC-based architectures profit from keeping data on the chip. I think most everybody knows that. So this will enable us to tackle the memory bottleneck, and this in turn will help to reduce latency and power usage. Our focus has been primarily on latency, but we saw that the power dissipation was also reduced because of this. And we focus on optimizing static memory planning during deployment. Okay. So just a brief overview of how TVM does it. We are using the TVM USMP, Unified Static Memory Planning. And first of all, TVM collects information about memory buffers in terms of buffer size, what are the conflicting buffers we have, what are the memory pool candidates. Here we use only 2 memory pool candidates, the SRAM and the DRAMs. And then buffers are assigned a static offset within one of the pool candidates, like individual buffers will have some static offsets. The conflicting buffers should not overlap, because if they overlap, then there will be that's not the correct deployment. Basically, you have to have the memory allocated for each of the buffers. We have to fulfill the alignment constraints, and target is defined by the algorithm. And in this case, this is the default flow in the TVM, which minimizes the workspace size. Okay, just a typical simple example. So this is the small, let's say, subgraph of the network, which has different buffer 1. This is the skip connection, and this buffer 2, buffer 3, and buffer 4. What happens is that the TVM memory planner sorts it by size, and you can see that if you have these sizes, it will sort the size, and then it will plan the workspace. So in the first case, it will first allocate the buffer 2, which takes the major space of the P1 workspace. I'm not right now using any term like SRAM and the DRAMs here. This is just a typical default use case, which I'm showing right now. Then comes the buffer 3, which, since if it has like 4, it can be occupied here, so it occupies here. And then there comes the buffer 1, which is occupied in the P2. And then the buffer 4 will come and it will occupy here, because these 2 will be over. There will be no more conflicts, and then the P1 can again be utilized. So this is just a 2 workspace model here. They don't have any, let's say, difference read and write speeds and so on and so forth. So this is just a plain, simple, similar workspace model we are talking about. Okay, this is the default flow in the TVM. Now in the deployment, what we did was that we tried to minimize the transfers through deployment. And in this case, as I said, that for in-memory computing, we have to reduce the DRAM transfer instead of the workspace size. The workspace size has to be reduced, but this was at a higher priority. And this takes up, this is the most important aspect which we have to focus on. We use the buffer information to reduce DRAM transfer, and we added new planning algorithms on top of the TVM Python interface. We did not try to get into the C part because that was a bit tricky to handle. And then we added some pre-processing and post-processing hooks for USMP to collect additional data and to modify the TVM IR module and finally to analyze the result. So in the pre-processing stage, what information we used is the lifetime, because this is a critical aspect primarily from the sake of skip connections, number of read operations and number of write operations, because this defines how much transfer you need to the DRAM and back. We need to reorder some layers, like first process layers, which reduces buffer sizes, and then we pin buffers which have long lifetime to DRAM. Let's say you have a very large skip connection, just move it to the DRAM, as simple as that, because this would block the SRAM for a long time, and this won't give you good performance. And then the post-processing. So the default memory planning algorithm focuses on minimizing workspace size. what I told you. So in the greedy by size, what you do is that the initial list is you have the initial list of the buffers, you sort by size, and then you pick from the list and try assigning it to a location in the candidate pool without overlap. In the greedy by conflicts, you sort by the number of conflicts. And the hill climbing is just a better version of the greedy by greedy algorithms, basically, but you can also have the objective function as size of the conflicts. In the new algorithms, what we did was we noticed that the existing algorithm performed decently. There was no problem in that. And for simple networks, like all approached to the same optimum results. But in the network which has a lot of skip connection, particularly in resonant-based architectures, this algorithm performed better. And we kind of use this objective function of transfer data instead of size. The transfer data is basically number of reads plus number of writes multiplied by size. And then we sort the list by the amount of transfer data we have, and then we do the greedy approach or the hill climbing approach. Okay, so let's go back to the previous example what we discussed before, and calculate the latency by the greedy by size and versus greedy by transfer algorithms. So this is the buffer. These are the two pools. Now we are complicating the problem a bit as well. We are giving the two pools as of the same size but have different read and write speeds. I think the read and write speeds for both the pools are same, but like they have the different read and write speeds. And this is basically the entire information which we have after the pre-processing. That they like the buffer 1, these are conflicting with these 3 buffers. It has size 3, it will do 1 write and it will do 2 reads. And so we have calculated all the transfer size as well. So the transfer will be 3 into 1 plus 2 into 3, it gives me 9. Okay. So let's do the greedy by size algorithm. So here the sort by size will do like this, where we have the buffer 2 as the top because it has the maximum size of 5, and so on and so forth. And this is what we discussed before. So the buffer 2 will go into P1, buffer 3 will go into P1, buffer 1 will go to P2, and buffer 4 will go to P1. Let's compute the latency here. So in the first case, the latency will be 5 because that's what we have here, plus 4 plus 2. That's it, right? From this simple operation. And the read will also be similar, 5 plus 4 plus 2. That's 11. So the latency is coming out to be 11. And for P2, the write will be 3 and the read will be 2 into 3, 6. So the latency will be 9. So the total latency will be 20. So this is the latency we are getting by the greedy by size, which gives you a good estimate. Now, if we do it by transfer, this table will change. This table will change in this way, that the buffer 2 will be as the top, but buffer 1 and buffer 3 will switch places. And now the new planning algorithm will do like this. After buffer 1, we'll put after buffer 2, we'll put buffer 1, and then we put the buffer 3 here. And then the buffer 4 will come here because there will have no conflicts here. And now we compute the write and the read latency. For P1, it will be 9.5. And for P2, it will be just 8. So the total latency will be 19.5. So just by using this approach, where we have sorted the list based on transfer, we kind of get like 0.5 improvement in the latency. And for networks which have lots of skip connections, we got good improvement in terms of latency. So we tried with the result-based architecture, then 2 intermediate NAS-produced architectures, and then the optimized network. And we can see that the transfer algorithms are giving better results than the size algorithms. And HCT, basically the hill climbing by transfer, gives the best result, and it should reach to the best result. In very simple networks, all of them reach to the best results. Yeah. So the summary and results. So in-memory computing based SRAMs to solve the memory bottleneck. We need tailor-made deployment to fully avail the benefits of IMC hardware. This gives us, by default, latency and energy improvement, and skip connections are handled really well here. Thanks.
Thank you very much. So are there any questions from the audience? This time we actually have questions for 1-4-22.
Thanks for the interesting talk. I'm just wondering, I mean, when you, in your algorithm, you're assuming that the transfer, I mean, it's an integer number for users. Potentially, let's say the amount it takes to do the transfer, right?
Correct.
So you're assuming that there's no dependency on the size of the buffer, right? Now,
No, we have to. We took that consideration.
Multiplies by size.
Yeah.
Then my question's answered. Sorry. Just to,
We have to take that, yeah, obviously.
Okay. Any other question? Great, then let's thank you again for a great talk. Move on to the next one. The next presentation is given by Max Sponner. Is it Sponner or Spooner? Sponner, okay, sure. Okay, same pronunciation, very good. So Max holds a diploma degree, which is equivalent to a master's degree in information technology from Technical University of Dresden. He's currently pursuing his PhD degree in computer science, also University of Dresden. His research focuses on embedded deep learning compilation optimization strategies with a focus on adaptive deep learning in embedded and heterogeneous environments. And what he is going to talk about, the title of the talk is MLIR, the non-augmentation framework for adaptive techniques in embedded applications. Thanks, Max. Go ahead.
Thank you. So, as already mentioned, we are looking into embedded applications. As I'm working at Infineon, the size of our embedded applications is basically target applications for Cortex-M-based microcontrollers. So we are running small cores at a couple of 100 megahertz with very small memories and the kilobyte sizes, and our storage is in this range as well. So the potential applications for us are mostly in monitoring sensor data and then detecting certain events on this data using relatively small deep learning models. And these applications can include healthcare, like monitoring of fitness tracking, industrial applications of all kinds, or a lot of smart home and smart appliances. And while most of these problems are relatively easy to solve if you don't have any constraints for your model sizes, so if you deploy in the cloud, you can quite quickly build models to solve these tasks. However, as we want to deploy to our microcontrollers, so our very resource-limited platform, we will run into a number of challenges when we now want to deploy our deep learning inference locally. The first one is to balance the model quality, so the prediction quality, mostly accuracy, and the resulting cost with our available resources and the requirements of our applications. So we are not only limited in terms of the available compute, but also we have other requirements like our worst case latency to ensure that our control loops are stable, for example, or that our user interfaces are usable and not frustrating to the user. Other constraints include the battery life of your wearable devices, or just the overall unit costs. That's quite interesting for our customers, of course. And lastly, we have the fast-moving field of deep learning and embedded deep learning. So we have increasingly complicated hardware architectures. We started out with just simple Cortex-M-based cores, and we added one NPU. Now we have multiple cores, multiple NPUs. The cores have instruction set extensions for vectorized processing and so on. Then we have the software side, so the toolchain landscape is permanently changing. Lots of stuff going on there. And lastly, we kind of have to keep track of the novel research on optimizations and other deployment strategies. And speaking of deployment strategies, we ourselves have been looking into adaptive deep learning. So for those of you who are not aware, that describes models that can change some of the hyperparameters at runtime without having to be retrained. So there are different techniques available. And the idea behind it is that compared to the traditional approach, where you have your model architecture, you find a quantization strategy that works, you have to find parameters that work across the entire range of potential inputs and also potential deployment scenarios. With adaptive deep learning, we have the advantage that we don't have to optimize for the global working point. Instead, we go for like a local working point, so we can adapt the workload to the current situation or circumstances, which means we can use the full model capabilities on difficult inputs while we save resources on the simpler data points. And in the embedded context, we usually have two components to such solutions. The first one is the reconfigurable model architecture, so the model that can change some of its hyperparameters, and some decision mechanisms that decides on how to reconfigure the model. We ourselves have been looking mostly into early exit neural networks. So this is a special kind of adaptive deep learning technique where we introduce so-called early exit branches into our model backend. And these branches are intended to perform the same task as the original output of our model, but due to their shallow position, we reach them earlier and at a cheaper cost. And the idea is that at runtime, our decision mechanism can decide which of these classifiers to use. And if one of these early exit results is sufficient enough for the current situation, we just skip over the rest of the computations, saving us quite a lot of time and resources. We went with this specific adaptive technique for two reasons. The first one is that such early exit architectures are quite a good match for the upcoming heterogeneous platforms and devices developed by Infineon. And you can also extend this idea to distributed platforms. So the individual subgraphs created by our introduced branches can be mapped to different accelerators or cores on our platform. And the second benefit is it's relatively easy to integrate with the existing ecosystem. So we can reuse most of the inference stacks and accelerator designs without having to maintain our own solutions that benefit some of the more exotic adaptive techniques. Now, how does PEAKS, our framework, fit into this? So PEAKS stands for Performance Enhancing Adaptive Execution. And what we wanted to achieve was to build a framework that kind of facilitates the necessary infrastructure to perform the rewrites on our model graphs to, for example, introduce these early exits. So it's in the first stage for us in our own work, a graph manipulation framework, which allows us to easily rewrite our network graph. And it facilitates the retraining and fine-tuning steps that are necessary to then fix our graph after we've, or our model after we have changed its graph, which is not really in the scope of established deep learning compiler tool chains. That's why we went with a dedicated framework for that. As most of our customers and most embedded deep learning engineers are not really aware of adaptive deep learning, we also implemented automated flows which enable these non-experts in the adaptive field, at least, to build efficient solutions by just utilizing the techniques we have established for their own use cases without having to know how an early exit network now specifically functions. And lastly, as a feature, we enabled PEAKS to be able to combine and chain these rewrite operations. So combine means we can apply multiple of them in parallel, and they will share some of the optimization artifacts if possible, to just save on resources. And a potential use case for that would be if you want to target a heterogeneous device fleet, if you either want to target multiple generations or SKUs of your product. And chaining rewrites just allows you to further optimize the performance by combining different techniques. And lastly, the accessibility was also quite important for us. So at least for the edge AI use case, we wanted to enable the developers to just use personal computer instead of having to utilize cloud or HPC resources. And at any step during the conversion flow, PEAKS allows you to create so-called summaries, which are just human-readable representations of what's going on with your model, what kind of information it was able to extract from your model, and why certain rewriting operations have been performed in these automated flows. So how exactly does PEAKS work? So roughly, you start out with your pre-trained model that you submit to our framework. And this model is then converted into what's called a model analysis object. And such an object then contains some base information about your model. We use two different graph level representations, extract some more base information about your architecture, the footprint of the individual layers, and somewhat abstract metrics. And it also creates the facility and infrastructure to enable the combining and chaining of graph rewrites. And as this information is not sufficient enough for most of the stuff that we want to do, the contained information can be extended with so-called reports, and they just encapsulate additional information, which is not always needed and often expensive to acquire. That's why we went with this modularized design and a lazy evaluation step. So if you submit a report to your model analysis object, it will only be created if it's needed. And you can either submit it manually, or it will be submitted automatically by these rewrite flows that I mentioned previously. Some of the reports that we've implemented so far are the hardware report, which is more or less just a wrapper for a performance model for your target hardware. With the open source release, we went with a rather generalized approach here. And these performance models should be able to give you layer-wise latency, memory, and storage estimates for their inference cost, and could also be used to check for compatibility issues between your layer configurations and your intended target devices. And that's on its own can already be quite helpful for developers, but also for the automated flows. It can allow them to tailor their found solutions to your hardware target, and also make sure that the found solutions are actually workable, so that the mappings work out and no illegal mappings of layer configurations to targets that don't work will be performed. Other reports are the dataset report, which currently is more or less an interface to give the training, validation, and calibration datasets to the flow. We built a broad interface. You can basically put in anything from Python lists to TensorFlow datasets. And these datasets reports can then be used by other stages to extract more information. For example, the accuracy report, which then just evaluates the model on the provided data. And that again can be quite helpful for the automated flows to limit the ranges within the search space for the potential solutions. And other reports are mostly just relevant for the automated rewriters or rewriting flows and not really on their own. Speaking of rewriting, so now once we have collected the information from our model analysis and different reports, we want to use it in our automated flows to create new solutions. For that, we implement so-called rewriters, which again, modular design encapsulate all of the necessary operations, and they can create one or more potential solution objects, which to facilitate our chaining of rewrites can be converted back into model analysis objects. And some of the functionality we have implemented so far are different kinds of early exit rewrites. As I've shown you previously, so in a histogram-based termination, that's quite interesting if you operate with a feed-forward network on a Tensor data stream, so some kind of sequential data. There, the tool selects an intermediate feature map to supervise, and as long as the changes within the intermediate feature maps are small enough, we just skip the execution of the full inference and reuse a previous result. So some kind of input filtering, basically. And for this publication, we also implemented right sizing, which more or less just reuses the existing early exiting infrastructure to permanently shrink the network graph to an earlier layer. So deeper layers can be pruned. And static slimming creates a set or ensemble of different risk configurations of your submitted model to make deploying to a heterogeneous device fleet easier. Then we have another special kind of rewrites, the compiler interfaces. And these are basically just there to directly compile through micro-TVM or TensorFlow Lite for microcontrollers. Now for the evaluation. So we used the current generation Infineon TSOC6 microcontroller for this experiments, and it's a Cortex M4F based core running at 150 megahertz. So we went in the evaluation with use cases that actually fit such kind of device. And the first experiment was the detection of myocardial infarctions from single ECG data. So that sounds quite difficult, but the intention is to enable smartwatches to detect heart attacks. And for a viable solution, it should be accurate, but as it's a variable solution, should also be power efficient to enable continuous monitoring over a long time with a single battery charge. For our input model, we went with a two-stage CNN from the related work. and the somewhat standard PTBXL dataset. And from its samples, we only extracted the data lead that corresponds to a typical smartwatch viewing location. For the rewrites that we applied, we went with our adaptive techniques and also the model slimming. The adaptive solutions were then compiled using both compiler interfaces, while the different slimmed versions were again chained up with the adaptive techniques before also compiling them. So each solution has been compiled using both compiler interfaces. And this allows us to compare the performance of both potential inference stacks for this use case. And yeah, just to summarize it, we plotted the latency in milliseconds against the accuracy. And one solution has the same accuracy, but depending on the inference stack, the latency is quite different. And as you can see for this specific use case, micro-TVM was able to outperform TensorFlow Lite Micro quite a lot. And the reason here is that TF Lite Micro is an interpreter-based approach, and with this rather small model size, interpreter overhead is quite significant. Now, speaking of the solutions that our Peaks framework created with its automated flow, you can see if we compare now the original network, if deployed through micro-TVM, with the combination or chaining of model slimming to 1/3 of its width. With the temporal early exiting, we can reduce the latency by over 90% with an accuracy drop of less than 3 percentage points. For the next experiment, we went with a wake word detection task. So the model needs to detect a word from a limited set of vocabulary. And that's a typical functionality for a somewhat limited instruction-based voice interface, or just the detection of the triggering word in your smart speaker. And as it's a user interface functionality, we want to achieve fast response times here. And for the model, we went with ARM steps-wise separable CNN in its largest configuration, just to follow the idea behind adaptive deep learning, that we want to get the best model that we can and just compensate for its additional cost with the adaptive reorganization of the inference footprint. For the dataset, we went with mini speech commands in its third iteration. So it's a bit larger than the original dataset. And as this dataset does not contain sequential data, which is used for some of our, or necessary for some of our contained functionality, we created artificial calibration and test sequences from the different splits of the dataset. And again, we applied multiple optimizations in parallel. Now we also added the right sizing, which permanently prunes deeper layers. And again, we changed it up with our compiler interfaces and adaptive techniques. Now for the first part of this experiment, we went with the official test split of the mini speech dataset. And interestingly, here the behavior between TF Lite Micro and micro-TVM is opposite. So now TF Lite is faster while micro-TVM is slower. And this has two reasons. The first one is now our model is much larger, so the interpreter overhead isn't as significant or barely noticeable. And the second part is that micro-TVM, for some reason, inserted a reshape operation before the initial convolution, which comes at quite the cost, as you can see. And that's why having different inference stacks as targets is quite helpful for us. And now looking into the automated flows and the created solutions, again, we could reduce the inference latency quite a bit by over half. So we went from 800 milliseconds to around about 300 milliseconds with an accuracy drop of less than 2 percentage points. And as we are operating on 1 second inputs with a certain overlap between our windows, you can see that in a real product that can be the difference between being able to build a viable solution or not. So such drastic reduction in latency can be quite helpful here. And now for the second part on the sequential data, again, the behavior between TF Lite and micro-TVM doesn't change. It's still the same base architecture. And the applied optimization, again, we can drastically reduce now our sequential data, our inference latency, no more than 80%. So that drops us down to less than 200 milliseconds on average, with an accuracy drop of less than 3 percentage points. Now for the conclusion, we have shown that Peaks is able to achieve quite significant latency gains, which should be able to translate into power or efficiency gains through race to idle or race to sleep concepts. And this was just the performance of our automated flows. So an expert might be able to further fine tune in terms of search parameters. It's now available on GitHub. And here on the right, you can see how such one of these human readable representations or summaries looks like for your augmentation flow. Yeah, thank you.
Thank you, Max. Yeah, panel is open for forum open for discussion. Are there any questions? Yes, more difficult ones.
So in your customer applications, does the variable latency of the early exiting have any impact? Because in the past, when I worked in automotive, it was like everything had to be deterministic.
Yeah, that's the benefit of working in consumer electronics. We are not as concerned with that. And for control loops, you have to account for it. But just for user interfaces, it's not really as relevant.
Maybe just to add on top of that, might be a bit of a stupid question, but when I saw this parts, well, the first example, sorry. So I saw that there was a latency of 5 milliseconds, and I was just thinking to myself, like, what difference does it make from an application perspective that I can detect a cardiac infarct for 5 milliseconds? You see what I mean? Like, it is genuinely interesting. Is there a difference, or is this, say, just a benchmark?
Firstly, it's a benchmark, but also if you can reduce the latency this drastically, you can often use it with some race to sleep concept. So you park your application for longer and using this to reduce your power consumption.
Okay, thanks for the great questions for the audience. Let's give a round of applause for Max again. We're coming to the last presentation for today, the last talk today. So the speaker can actually not be physically present. So he will be on the Zoom call. He has recorded a video in case there might be any problems with the connection. So we're going to play the video. He will be on the call. And as we see, it's already waiting in the Zoom call.
Yeah.
And then afterwards, we were going to take questions directly live from him. So the next speaker is Ananda Samajdar. He worked with IBM Research in Yorktown, United States. He graduated from Georgia Institute of Technology in 2021. He has a lot of professional experience among working with IBM Research in Yorktown since 2002 as a research staff member. So his talk is on co-optimizing algorithms, hardware, and software for AI acceleration, the IBM Perspective.
Hello, everybody. Thank you for staying along. I'm Anand. I work as a research scientist at IBM's T.J. Watson Research Center in New York. In today's talk, I want to talk a bit about our team's effort in enabling AI acceleration through co-optimizing computing across the stack via algorithms, hardware, and software. The contents of this slide are works of many of my talented team members over the years. However, any opinions I present in this talk are my own and does not reflect IBM's stand, official or unofficial. Without further ado, let's get started. I know I'm preaching to the choir here, but I think we all agree that over the last few years, AI has captured everybody's imagination. Be it the optimist who see it as a technological watershed moment, the realist who acknowledge its power to transform our workforce and our society, or be it the pessimists who are worried that humanity will not be able to control the effects of AI systems in various contexts. We as systems engineers/scientists are cognizant to a very different kind of challenge though. This chart is from OpenAI. It's a bit old, but it does provide an excellent insight on how much raw compute power is required for training of more and more powerful models. In fact, language models are even bulkier and are challenging to both train and perform inference on. A decade ago, when AlexNet kicked off the DNN-based machine learning, we were in the domain of single task or narrow AI. Now with generalized chatbots like ChatGPT, we are in the domain of broad AI. It is not a stretch that in near future we will see models capable of learning in even broader contexts and modalities, making strides toward generality. To cater to ever-growing compute, it is imperative that we innovate across the stack on application and mathematical algorithms, specialized hardware, and the software stack to support it. Turnaround time-wise, some of these advances can be implemented and iterated on rapidly, like algorithms or in application domain, while advances as devices, microarchitecture, or programming model take longer time to incorporate. Over the years, however, we at IBM have been able to create solutions across these stacks, which I will cover in the subsequent slides. This talk is organized in 3 broad parts, starting with the innovations in algorithm side, especially in low precision approximate computing. Then I will cover the design of our AI hardware, and finally the compiler infrastructure that we build that keeps it all going. Machine learning workloads show resiliency to approximation, which provides us with a unique opportunity to pack more and more compute on the same real estate. Models can be tuned pre and post training to lower bit widths to recover accuracy and to get quadratic increases in throughput. Interestingly, in fact, scaling data width does not require any significant hardware or data flow changes. However, various models and deployment use cases have different precision requirements, which systems designers like us should keep in mind. Like I mentioned, precision scaling provides quadratic improvement in throughput. Our team has depicted extreme precision scaling over the last few years while maintaining the ISO model accuracy. Some of our published results show up to 4-bit precision scaling in training, while for inference, we showed that 2-bit precision scaling is possible and we can exploit sparsity even with 4 bits. In contemporary commercial systems, FP16 and Int8 are the most widely used choices for inference. While conversion to FP16 from FP32 requires direct quantization from the trained model, Int8 deployment has some challenges. First, the activation and auxiliary operation are needed to be performed in floating point representation, either in FP16 or FP32, to preserve accuracy. However, for matmuls, we need to perform quantization from floating point format into Int8. And this is done opportunistically, mostly in 2 ways. For static data structures, we do post-training quantization, and in this case, we do some ahead of time conversion. For dynamic data structures, however, like output of the auxiliary ops, we have to perform on-the-fly conversions. If model tweaking is possible in any way, in that case, we can recover some accuracy by doing quantization-aware training. IBM Research has invented and published a couple of very interesting techniques to enable inference at ultra-low int4 precisions. The packed method describes using gradient descent to determine the optimal clipping level of dynamic data structures like activations during the training time. This clipping level is then applied at inference time to compress the dynamic data structures such that the computation and quantization errors can be minimized. Another method called SAWV, which is the statistics aware weight winning, uses the distribution of the weight tensor to determine a scaling factor. So for instance, in this graph, you can see that for the various different distributions, we come up with a particular scaling factor. With this scaling factor, the quantization error is minimized. If you are interested for more, then I highly recommend reading the SysML 2019 paper, which show how these techniques can be used in combination to obtain near ISO accuracy during inference when using 4 or even 2-bit widths for static and dynamic tensors. Going to such low precision, however, comes with a unique set of challenges. Like under-provisioned models like mobile nets, they are harder to quantize to near to ISO or near accuracy. Then it is hyperparameters are expensive to discover, and also some of the layers of the network, like 10% of the layers which have activation functions or some auxiliary functions have to use higher precision to guarantee accuracy. Of course, the training times are longer, and then incorporating sparsity with this ultra low precision format is a difficult task if you want to be in ISO accuracy. Supporting multiple and reduced precisions is at the heart of the efficiency of our AI systems. I would now like to talk about our accelerator, which incorporates our techniques, and show you the general architecture of it. The basic block of our design is this rapid core. It is a data flow machine with a 2D PE array which supports FP16 and lower precisions. It is constructed as an 8x8 array with an 8-way SIMD MAC and a local register file in each PE. And input can come from west or north neighbors, and the data can move to either towards east or through south neighbors like in a systolic array. We also have a 1D array of special functional units which perform FP16 and FP32 vector linear or nonlinear applications. And we have 8 slices connected to each PE array column. So when we use it in an FP16, it becomes an 8-way SIMD, and in FP32 precision, it becomes a 4-way SIMD. And then it also supports a cross SIMD reduction. We have directly addressable multi-level scratch pads, which are accessible from each of these compute elements. And these all compute units are programmable. Now, given that it is a deterministic workload, we can create consequent threads of execution for each of the compute unit. And our compiler creates things like different kind of programs like data sequencing programs, which do load store of data from the scratchpad, or data processing programs, which are doing the heart of the computation and define the computation sequence. The beauty of the basic architecture and the programmer model is that it could be scaled to multiple use cases, like integrating it into a single coprocessor format in the IBM Telum, which you see on the left side. Or it could be made into an SoC form factor, as we have done in this card, in the AIU card, which I'm showing on the right, which can sit on a PCIe bus. The same basic architecture and the compilation framework, along with some system-level software changes, also enable us to use the AIUs together in form of a cluster. As you see in this picture, this cluster, we have it up and running in our Yorktown lab. If you are visiting our lab anytime, please check it out. It's beautiful, and to be honest, it's very, very cool. I would like to do a little bit of a deep dive into this 4-core AI chip that we called a Rapid, which is basically a 4-core version of the baseline architecture which I've shown before. So this is a 4-core accelerator chip fabricated at 7 nanometer, and we presented it at ISCA 2021. So this guy works at 1.6 gigahertz and can get up to 16.5 teraflops per watt, doing 102.4 teraflops at INT4. It is also capable of supporting multiple precisions. For instance, it definitely supports FP16, and it supports 2 flavors of FP8 with some programmable bias, INT4 and INT2 formats as well. It also does sparsity aware clock throttling, so that it can save some power if there is sparsity present in the workload. This slide presents some key architectural features of the Rapid core. So first of all, like I mentioned before, it supports mixed precisions to obtain the maximum benefit of performance and efficiency. It supports end-to-end coverage, application coverage with the special functional unit, and support for data shuffle operations. Then the SFU also supports the auxiliary operations so that it can balance the throughput between convolution and gems. And this is very important because otherwise what happens, like if we create an accelerator only for the hefty gem operations and everything, although the gem operations do tend to get accelerated, the data movement from host or some other auxiliary device to the accelerator kind of kills the performance. Like I said before, we also have sparsity-aware frequency throttling. So what happens in this particular case is that at the compile time, the sparsity analysis is done, and then as the stall rate is calculated. And with this knowledge, when the device is programmed, power throttling is applied through zero gating or frequency modulation so that we get some power efficiency back. And finally, since it is a multi-core system, it definitely has this unique innovations for unicast and multicast data transfer between the cores. And then I will show it later, but it has implicit producer-consumer synchronization for easier, multi-core lets us do efficient mapping, and the implicit synchronization makes it easy for the programmer to map computations into various cores. The special functional unit, as I have mentioned before, it supports a wide variety of aux-ops in FIT16 or FIT32, both in forward and backward pass. So rapid core can theoretically do backward passes itself. So activation functions like ReLU, leaky ReLU, sigmoid, tanh, they are all supported. And since these components are programmable, it could be extended to newer operations which we have not seen before. We also have a slew of normalization functions like batch norm, mean, softmax that are supported. Pooling operations are of course supported here, and then some data shuffle operation, quantization operations are also needed to be supported that the SFU enables us. Moreover, the creating this kind of architecture is comes with pretty unique challenges. For instance, we have limited real estate per core. Now we have to balance the MPE versus the SFUs because we want to make sure that the computation there are no control hazards coming because either there are like too few MPEs or there are too few SFUs to consume the data generated by the MPEs. Also, with more and more compute units being packed, we have to do the L1 capacity to compute balance just to make sure that everything is fed and humming, and there is no implicit memory bottleneck we have in our cores. For multi-core scaling, we have a bring interconnect to communicate between cores and memory. And then an important factor which enables us to seamlessly support multi-core mapping is the memory network interface, which is a programmable unit to facilitate data communication. So basically in memory network interface, we have two kinds of programmable units. One is called MLIR, which handles and orchestrates data which is incoming to the L1 scratchpad for each core, and the SU, which is the store unit, which does the orchestration for the data outgoing from L1 scratchpad. And because these are programmable, they allow multiple outstanding requests to memories, neighbor memories, or to the global memory, and then also it allows us to track out of order data returns. Again, an efficient multicast and implicit producer-consumer synchronization enablement has been done. It's I think it is a pretty neat invention which goes into the product. So what happens is that we have something called a request aggregator, right? That combines requests from multiple producers and consumers for efficient multicast. And then the implicit producer-consumer synchronization happens because we know that the number of participating consumers is at the compile time. So what we do is that the data, both because we know the data movement pattern right at the compile time, we can program both the consumers and producers to make data requests as and when they need to receive or send them, and the request aggregator can capture all of that and then send out one multicast at a time. And because of the deterministic nature and because of the efficiency on the multicast, even on a ring, we can allow simultaneous multicast across overlapping core groups, which basically practically eliminates the any congestion on the ring, allowing for heavier compute to go across multiple cores. And then it also enables us to scale the design very efficiently. The high programmability of the rapid architecture opens up a lot of possibility to innovate in the software stack to make it scalable. And while there is so much complexity in the hardware itself, we have to make sure that the programmability is simple. So in the next few slides, I'm going to give you a glimpse of our software stack. It is absolutely critical for the software stack to be robust, right? Our compiler stack Deep Tools is built in a way such that it can support variety of software frameworks like TensorFlow, PyTorch, etc. While it also has to be extensible to extract performance across multiple cores when we scale to different generations or form factors. For instance, the compiler is built to perform multiple levels of optimization. So we do optimization at the graph level, the node level, and then these graph level and node level optimizations are done in the front end, and in the back end, in the code generation step, we do a lot of programmable optimizations. Our since it is a multi-core it's a multi-core system, it creates a unique challenge for compiler as compared to some other contemporary products which we have out there, which means the optimization space has to match the data movement and the compute speeds at different memory levels to ensure high utilization, while avoiding any kind of stalls that is introduced because we have to map to different cores, and then these cores have to talk to each other. If you guys are interested to learn more, I would definitely recommend looking at this paper which came out in Micro, IEEE Micro sometime back, and please, I am also available for any questions on the front-end side if you are interested. In the compiler front-end side, there are some key innovations which went in to make our front-end efficient. I want to talk a little bit about those here as well. So first of all, a lot of thought went into designing the configuration of the design switch itself. So we needed a compact configuration which is very expressive, like it should be able to capture data flow, the data staging parameters, the loop order, the workload descriptor dimensions, etc., which can basically tell us how which can basically express and tell us the entire space of expressing mapping the workload into multiple cores and then multiple levels of optimizations we have. But it also has to be compact, otherwise the exploration space kind of grows exponentially. We also built a custom waveform estimator, a waveform based configuration estimator, which is our cost model. This waveform based estimator is capable of estimating compute and memory behavior quickly without the need of outright simulation, while also exposing overlaps between memory and compute at different loop iterations, and what kind of opportunities we have to extract performance by tweaking our configuration space. And finally, the compiler kind of works using the design space explorer, right? It is the methodology to search the configuration space. It is a heuristic-based, search-based approach, where we are doing optimizations at multiple levels, as I've mentioned before. So this explorer basically sweeps the configuration space, then evaluates and prunes redundant or non-performant configurations fast, so that the compilation time is also low, while we get to a reasonable configuration in this multi-core machine very soon. So in the back end side, we use MLIR to capture and describe the transformations. Internally, MLIR is extended for our custom for creating our custom IRs to implement the explicit decoupled data orchestration paradigm, the ADDO paradigm, to keep it extensible to different generations of the rapid architecture, and it also makes it more expressive. And then there are multiple different innovations which have gone into code compaction and whatnot, so that our this behemoth of a machine, which is very highly programmable, can be programmed and kind of deployed at a realistic timeline for every new workload that we see. So that brings me to the end of my talk. Even a decade later, it seems like we are at the precipice of the AI age. None of these advances are possible without hardware and software co-design, and we have to optimize across the stack. there is still tremendous room for innovation. Please feel free to reach me out if you're interested in what we do. We are very excited to talk about what we are doing, and we are always looking for talent. So if you think that what we are doing is cool and you would like to either contribute or just know about it, do reach out to me or any of our team members. And thank you very much for your kind attention. With that, please enjoy the rest of the workshop. Thank you.
Hello, Anand. Now we should have you live in the Zoom call. Can you hear us? We are.
Stop sharing.
Hi, Michael. Hi, can you hear me?
Yes. Thank you for your great presentation. You already got a big round of applause. Maybe you heard it on YouTube, or we'll hear it in 30 seconds. Okay, we'll take a round of question and answers from the audience. Maybe I'll pass the microphone on to Andreas.
Do we have questions?
Can you elaborate a bit on the optimizations based on the waveform? Because I didn't really understand what the waveform in this context means.
So I will repeat the question, maybe it is not. So could you elaborate on the waveform? The person asked the question couldn't really understand what a waveform is about.
I see. I see. Yeah. Yeah, that's I think I covered it in a very small time window. So this is the waveform-based cost model is trying to estimate given the what kind of design parameters we have, right? Be it per core mapping or the workload parameters, that how the compute and memory would overlap for every loop iteration. So one way of figuring out that information is to do outright simulation. But since this is compilation and we have to do a lot of iterations, we have to come up with the accurate enough descriptor where we can see the overlap between the compute and memory movements. Um, I mean, compute and memory movements, but not go all the way to cycle level. So the waveform is like pseudo analytical, pseudo cycle level, intermediate way of figuring out the cost of each of the configuration. And like if you go to the finest granularity, probably it becomes a cycle accurate simulator, but we are working at a little bit more coarser granularity to estimate that at every loop level, every loop iteration level, how much time we are spending in compute and how much time we are not.
Okay, thank you. Any further questions?
No more questions?
Yeah, there was one.
Sorry, one more question.
Hey, Anand, I'm not sure whether you can hear me, but nice to see you. Since you showed this very nice machine that's at the Auton Center, do you actually use it also in production, or is it mainly the research cluster that you are working on for researchers?
Oh, that's Moritz, thank you. I mean, I have showed the pictures, right? So, production wise, as in if we are selling it to customers or not, I cannot really tell. But our AIU is like one of the hottest things coming out of research. So we do have it running up and running in the lab as a cluster. So it could be used for customer use cases. Like we can, I don't know, it's now a business question that whether this design should go with this kind of software architecture which we have built. But it is handling all kinds of real life workloads. So we are like language models, for instance, like we do benchmark for all the latest and greatest things which are coming in strict SLA guarantees to make sure that our both hardware and the software toolchain is robust.
Thank you. Any more questions? We have time for a short one. Okay. If not, totally fine. So let's give another round of applause.
Thank you, everyone. Thanks.
And thank you very much for taking the time to participate remotely.
Thank you, Michael. Pleasure's all mine. Thank you.
Okay. Thank you. Bye. Okay. Then this was our last presentation. Please do not leave yet. Give us 2 more minutes. So we have one, we have one more item. Huh? Just. So, like it is tradition in the last 2 editions of Kodai, we also have a Best Paper Award. So the Best Paper Award this year goes to Shreya Alladi for her work on insights into interpreters, compilers, and optimizers for neural networks. Let's give her a big round of applause for the great work. Yeah. Congratulations. Okay. Okay. You want to say 1, 2 words? Please. You don't have to. You don't have to.
Thank you, everyone. That's what.
Okay. That's good enough. Okay, then that's really the end. Thanks everybody for coming here today. Everybody who gave a presentation, everybody who helped, everybody who listened. We're looking forward to the next edition next year. Please come again and have a great day.
Also some more photos, yeah.
Yeah.